Hi, Jyoti, can you hear me?
Let me see. I think I have to unmute. Yeah, I think I can hear you. Yeah.
Good. So, okay. So,
Okay.
Hello. Yeah.
Hi. So maybe we could follow this thing that to the extent possible, all
The
half.
time.
Yeah, right. So it's 25 plus 5, 13 plus 2.
Yeah.
So
Right. So basically, there are 3 talks in this session.
Right.
And all of them are half an hour.
Exactly. Absolutely. Right. Yeah.
So we'll try to do it 25 plus 5.
Right. Right. That's right. Thanks. Thank you.
Look, the discussion session is how long?
It's up to you. Maybe half hour, 45 minutes.
Yeah. Some cutoff has to be applied.
Yeah, right. So I mean, you decide. It's entirely up to you.
So let's see how the response is. Okay.
Right. Exactly.
Okay.
So I have posted your topic, Professor Maharana. I've posted your topic at the schedule. You can see there is a double asterisk on the schedule, and it says
start the ball rolling.
yeah. Right. Yeah. So yeah.
Okay.
All right. So our speaker is here already?
Yes, sir.
Okay. Yes. So do you want to wait, Alok, do you want to wait for a couple of minutes? Because I can see only half the population. Like there were like 92 people.
Yeah, right. Yeah. Plus, I venture to push people have a really quick lunch. I don't know. So yeah, I mean, maybe we could wait for a few minutes if that's okay.
Hello.
Yeah. Hi, Abhishek. Yeah.
Hi. My screen is visible, right?
Your screen is visible. Yes.
Okay. And yeah, thank you.
Maybe you can make it like full screen because we can also see the sidebar.
Oh.
Yeah, you can get rid of the sidebar by clicking on one of those arrows, I think.
I think that's the best I can do. Oh, right.
Yeah.
This is better?
This is perfect. Yeah. Yes, Abhishek. So you'll have like 25 minutes, and I'll give you a reminder after 25 minutes. And hopefully you'll finish by then, and then we'll have like 5 minutes of questions. Okay.
Okay. Okay. So I should begin now.
Yeah, maybe 2 minutes we have waited. Maybe we can start because the recording is already there. So what do you say? Hello?
Bilkul, you please, you decide. Jyotirmay, please, you're the boss. You decide.
No way. Okay, maybe we can start. Okay. So welcome everyone to this post-lunch session of the first day. So our first speaker in this session is Abhishek Mehta from IIT Pune, and he will be telling us about parity-odd 3D CFT three-point functions and flat space scattering amplitude correspondence. Abhishek, please start.
Yeah. Good afternoon. Thank you for giving me this opportunity. So I'll be speaking about this new parity-odd correspondence. Actually, the CFT correlator and the flat space amplitude correspondence has been studied in Mellin space by Penedonus, Kaplan, Raju, Fitzpatrick, and it has also been studied in momentum space to a degree by Raju, Farrow, Lipstein, and 𝗏𝗏𝗀𝗏. And even though this is a very well studied correspondence, we still have a lot of interesting new results to present in this talk in the momentum space. And momentum space CFT has not been very well studied up until recently. And this talk is actually based on an upcoming paper which I am writing with my supervisor, Professor Sachin Jain, and a paper which we already wrote with Professor Sachin Jain and Ranjan John, Amin Nizami, and Aditya Suresh. Right. So let's begin with what we already know about 3.4D flat space amplitudes and 3.3D CFT correlators. Just as a note, these amplitudes which we are talking about are actually arbitrary spinous massless gauge fields, cubic amplitudes, and the CFT correlations are for conserved arbitrary spinous currents. And in the amplitude side, we have actually two parity even and two parity odd structures. And we also see a double copy relation amongst the cubic amplitudes. The Yang-Mills graviton double copy is very well known, is one of the double copy structures that is very well known. But on the 3D CFT side, we see that compared to the 4D amplitude, we have two parity even and only one parity odd structure. So compared to the 4D amplitude, we have one structure missing. And a priori, we do not see any double copy structure manifest at the level of the CFT correlators. So the aim of this talk is to actually make the map, or rather the correspondence between 4D amplitudes and 3D CFT correlators, at least at the 3-point level, more precise. And to do that, we construct the missing second parity odd CFT structure and establish a double copy structure in the CFT correlators. Right. So let me just get some of the conventions and notations out of the way. So when we are working in 4D momentum space, I am actually, to make the correspondence between the 3D CFT correlators and the 4D cubic vertices, the correspondence between them more manifest, we work with the following parameterization of the polarization tensor and the null momenta. And in these parameterizations, the momentum conservation looks like this, and the various 4-dimensional Lorentz invariant structures, they look like this in this parameterization. Now we can take a look at a simple photon-photon graviton vertex in the 4D side. There are four independent structures on the 4D side. Non-minimal vertex with its parity-odd and parity-even substructures, and a minimal vertex with a parity-odd and a parity-even vertex. And for this case, the minimal derivative is a two-derivative vertex, which, for example, a two-derivative vertex will be √G(f²). But in general, for arbitrary spins, it's a S3 plus S2 minus S1 derivative. Keep in mind that S1 is less than equal to S2 is less than equal to S3. And similarly, the non-minimal vertex is actually a four-derivative vertex in this example, but in general, it can be a S1 plus S2 plus S3 derivative vertex. Yeah, I am working in momentum space, but yes, in position space, they have these derivatives. Yes. So for arbitrary spins, the cubic vertex look like this. They are basically powers of some Lorentz invariant structures, which I have mentioned here. And for S1, for the case of S1 equal to S2, we actually have to make use of some Schouten identities to write it in a nice way. And if you were to work with these cubic vertices play around with the spins, you will notice the following double copy structure for in the case of spin 2 and spin 1 amongst the cubic vertices. And this is very much like the double copy structures we know between Yang-Mills and Einstein. Yeah. So what about CFTs? In CFT, like I have alluded before, that we have two parity even structures and one parity odd structures. And now we see that we do not have enough structures on the CFT side to establish a precise correspondence between correlators and 4D flat space vertices or amplitudes. And the aim is to remedy this by realizing the one extra parity odd CFT 3-point structure and a double copy in the CFT side. To do that, I and my collaborators found it very convenient to introduce a new substructure to the CFT correlators. Here we break a CFT correlator into what we call a homogeneous and a non-homogeneous component. And a homogeneous and the non-homogeneous component behave very differently when we use the special conformal word identities. We see that for the homogeneous case they vanish, and for the non-homogeneous case we get the transverse word identity terms. And notice that we are working in the momentum space here, because in position space such a distinction is generally not done, because at non-coincident points these word identity terms will vanish, because in position space these word identities have delta functions in them. And we have found that this is a very natural way of looking at momentum space correlator, and we have also observed that this is best implemented in spinor helicity variables. And this homogeneous and the non-homogeneous components, they seem to have some physical meaning, and that physical meaning is made manifest when we look in the CFT3 DS4 correspondence, where we noticed that the homogeneous even is provided by the W cube interaction in the bulk. The non-homogeneous even is provided by the Einstein gravity part, and the odd homogeneous terms are provided by W square W tilde parts. Basically, what I'm trying to say is that these homogeneous and the non-homogeneous components have one-to-one correspondence to one of the vertices in the DS space. So once we have the homogeneous and the non-homogeneous distinction of the CFT correlator very clear, we will see that even the flat space limits of the CFT correlator becomes cleaner. And what do I mean by that? So the flat space limit of any d-dimensional 3-point correlator will give you a d+1 dimensional flat space cubic vertex. So for d equal to 3, we will have a 4-dimensional flat space cubic vertex. So if we again take our favorite example of spin 1 and spin 2 correlation, the parity even homogeneous and the non-homogeneous structures look like this. And if we were to take its flat space limit, which is given by E equal to 0, we notice that the leading pole of these homogeneous and the non-homogeneous components are basically the minimal and the non-minimal amplitudes for photon-photon graviton coupling, cubic coupling, and parity even minimal and non-minimal coupling. And for the homogeneous or parity odd homogeneous structure, the flat space limit gives a non-minimal parity odd cubic coupling for graviton-graviton photon at the leading pole. Now we see, now we discussed that any 3-point function has only 3 structures, and we seem to have exhausted all the 3 CFT structures, and we have already related them in the flat space limit to 3 of the 4 4D amplitudes. So we have one amplitude still missing, which is not a flat space limit of a JJT correlation structure. So the general observation we see is that non-minimal odd is a flat space limit of a parity odd homogeneous CFT structure. A non-minimal parity even amplitude is a flat space limit of even homogeneous CFT structure, and so on. What is missing is the minimal odd, which doesn't seem to come from a flat space limit of any CFT 3-point structure. And therefore, in order to ascertain the missing parity odd structure, we need to understand the flat space amplitudes and the CFT correlator better. And what do I mean by that is that we have observed that the flat space cubic amplitudes have a map between parity even and parity odd structures, and that is what we call the epsilon transform. And the epsilon transform is a differential operator, and it is implemented this way. And more precisely, it takes even minimal parity even minimal structures to parity odd minimal structures, and non-minimal parity even structures to non-minimal odd structures. And we can take a look at a very simple example that this epsilon structure works very well, and it also works for arbitrary spins. And we also noticed in our studies that this epsilon structure can in fact map parity even homogeneous 3-point correlations to parity odd homogeneous 3-point correlations. And notice that if I were to take a flat space limit of 32, remember that I said that CFTD correlators in the flat space limit reduce to d+1 dimensional cubic amplitudes. We will see that we will reproduce, oh, sorry, the equations are wrong. We will reproduce equation 29. We will reproduce equation 29. And therefore, if we wish to reproduce 28 as a flat space limit of some CFT structure, I have to propose a new map which between even non-homogeneous structures and odd non-homogeneous structures. Remember that there were only 3 structures in a CFT correlator, that is even homogeneous, odd homogeneous, and even non-homogeneous. And we have to postulate a new structure which is related to the already known even non-homogeneous structure, and they're related by this map. They're related by this epsilon map, and we see that this odd non-homogeneous structure is precisely the new CFT structure we need to reproduce the minimal odd amplitude in the flat space limit. So how does this new CFT structure look like? Well, I have an example for you. Again, we stick to our obsession with spin 1, and spin 2 correlation, and this is how the new parity-odd structure looks like. But this CFT structure has some peculiar properties that we will see here. If we were to look at this structure, the word identity of this new structure in Poisson space, we see that there are no delta functions in it, or rather at non-coincident points, this is non-zero. This object del1 mu of this object is non-zero compared to the already known non-homogeneous even structure which has these delta functions, and this T is a conserved current. But for this new structure, this T mu is some spin 2 current which is non-conserved, and this is the main reason why this structure, we missed this structure in Poisson space, because when we are computing correlators, Poisson space correlators, we impose the current conservation for correlations of conserved current, and therefore that is the reason why we missed it. And for arbitrary spins, the general proposal is as follows: that in the flat space limit, the minimal odd vertex will be reproduced by this new non-homogeneous odd CFT structure. And more precisely, this non-homogeneous odd CFT structure is the epsilon transform of the already known homogeneous, this is parity even structure. Yes. Now in the Jain and in a combined study by Professor Sachin Jain and Dr. Ranjan John, they came up with a very interesting relation between parity even and parity odd structures to the already familiar structures of the CFT, namely the free boson correlators and the free fermionic correlators. At the level of the 3-point function, they were able to establish these following results. And the new CFT structure, which I discussed, can be written in terms of the familiar CFT structures as follows. It's just the epsilon transform of free boson plus free fermion by 2. And now we actually come to the final part of my presentation, that is the double copy structures in CFT3. Since we know that CFT3 correlators give 4D flat space QB vertices, and since these cubic vertices show some double copy relation, does it imply that the CFT correlations also show some double copy relations? Well, in Farrow and McFadden, they understood a double copy relation in this flat space limit, and they used it to suggest a double copy relation beyond the flat space limit. But given the complicated structure of CFT correlators in momentum space, it is not very clear, and it seems unlikely that such a double copy could exist in general. And we of course know that such a relation doesn't hold in Poisson space. Am I still audible to people? Hello?
Yes, you are audible. Yes.
Okay,
Please
thank
continue.
you. Yeah. So yes, in our studies, we have understood these double copy structure of CFT correlator in this combined collaboration, and we have been able to extend this parity or this double copy structure to parity violating terms as well. And we are going to see how this homogeneous and the non-homogeneous structures which we identified in a momentum space CFT correlator will be very crucial to our understanding of this double copy structure. So suppose you consider a double copy structure of this kind, because we know that a 3-point function has only 3 structures, 2 parity even and 1 parity odd structure. A double copy relation of this kind would mean that the RHS will have 4 parity even and 2 parity odd structures, because if you just square it, you will find there are 4 parity even and 2 parity odd structures. And you see that there is a discrepancy in the counting here, but this can be remedied very easily if you were to consider a different form of a double copy, where the double copy is only amongst the homogeneous and the non-homogeneous structures of a CFT correlator. Because if we were to do this double copy, a square of the RHS would mean this expression, and because even square is just the same as odd square, which we were able to understand, it means that out of these 3 structures, only 2 are independent, and therefore the counting of the independent structures on both sides match, and the discrepancy simply goes away. So based on this understanding, we have been able to generalize the double copy relations to arbitrary spins, and the result is here as follows. For both homogeneous and the non-homogeneous components, the double copy relations hold separately, and these double copies, unlike discussed in McFadden and Faro, they hold even beyond the flat space limits. So these are exact double copies. They are not flat space limits. They are exact double copies. And I can provide you an example for S prime for the double copy relation between JJJ and TTT, and they look like this. And yeah, we also have similar relations for arbitrary spins. So in conclusion, this has given us a lot of ideas and motivation to think about double copy relations for higher point functions like 4-point functions, and probably make a path for spinor helicity bootstrap maybe, and think about flat space limits for higher point function and see whether they give quartic vertices in the flat space limit, and explore the supersymmetric theory for similar correspondences. I would like to finish my presentation with a puzzle. In 3+1 dimensions, it is known that there is a discrepancy between the amplitudes, the non-perturbative amplitudes, and which are computed entirely based on the symmetries, cubic amplitudes, non-perturbative cubic amplitudes, and the local cubic vertices. But interestingly, for some CFT correlators, as we have seen that these flat space limit always goes to the tree level cubic vertices, these cubic vertices. But if we look at CFT correlators that are outside the triangle, what I mean is that the spin 3 is greater than the sum of spin 1 plus spin 2 in a 3-point correlation. The subleading terms in the flat space limit of such outside the triangle correlators will reproduce the full flat space amplitude, full non-perturbative flat space amplitude. And thank you. Questions?
Yeah, thanks a lot, Abhishek, for a very nice talk. Are there any questions and comments? We have some time for taking them. Yes, I can see some hands. Yes, Shiraz. Yes.
So I joined your talk a little late, so forgive me if I've misunderstood. But you said in the TJJ, I suppose, that there were not 3 but 4 independent CFT structures. Did I understand you right? So 4 independent kinematical structures.
Yes,
is that right?
Is right. Yes.
Is one of them, is the new one a contact term, or does it also persist at separated points?
It's not a contact term. It does persist at separated points. Yes. The new structure. Yeah. Because as I showed the Ward identity, if it were a contact term, it would, even its Ward identity wouldn't persist, right? So
right. So why doesn't this, if this is right, why doesn't it completely change? I think my memory is that the 𝗲𝗂𝗃𝗃 analysis was, the starting point of that was that there were only 3 structures for conserved currents.
That is correct. Yes.
And you say there is a 4th structure which persists at at separated points. So it sounds like it should completely change that analysis.
Because the 𝗲𝗂𝗃𝗃 analysis was based on conserved currents, but this Ward identity for this new structure shows that the T is not a conserved object. So it will not come up in the analysis by 𝗲𝗂𝗃𝗃.
I see. So, but then it is not a structure for a conserved stress tensor.
That is correct. That is absolutely correct. Yes.
Oh, I see. Fine. Okay. But then, I mean, why is it relevant to gravitational scattering, for instance?
Because this flat space limit produces the flat space limit of this object produces the minimal parity-odd cubic coupling. So in that sense, it is relevant.
I'm sorry to persist, but if you had a, you had a graviton in the bulk, the corresponding stress tensor would be conserved, right?
That is right. We have not thought from that perspective yet. The bulk interpretation of this new structure. So yeah, I don't know.
Yeah, I don't think it will persist from the bulk perspective. It was just to point out that, in the flat space, there are this 4th structure, how to construct that, which correlator in the flat space limit gives the correct 4th structure in the 4th flat space vertex, which was not understood. This was just to, as it is clear, it's not conserved. So in the bulk, it will not play the role. You are totally right.
Oh, I see. So is the statement that if you take a non-conserved stress tensor and 2 conserved currents, then instead of 3 structures there are 4? Is that one of your conclusions?
Yes.
At least the parity-odd thing, there is one more that one can define like this. Maybe there are more general structures that we may not have thought. The interesting point of these structures are that they can just be constructed out of the free theory by doing a simple epsilon transformation.
I see. So you can find examples of new structures, but there could be more. I see. Thank you. In general, if you take spin S1, spin S2, spin S3, without any conservation, you'd expect the number of structures to grow fast with S, right? Some power of S. Isn't that right?
So yeah, that is right. But it is like, it's exactly like the non-conserved current in 𝗲𝗂𝗃𝗃 sense that, they are even non-conserved if they are not even higher spin non-conserved thing. They're in that sense, that they're just constructible out of free theories. You're right that one should be able to construct more. Yeah.
Okay, thank you.
Yeah. So Arindam, do you have a question?
Yeah, so I had a similar question actually. So at one point you were Abhishek, you were relating these structures with using DS4-CFT3 correspondence to different vertices in the here, right?
Yes.
So now that you have a new structure, how do you? I mean, how does it in this interpretation? How does it look like? I mean, like what?
Yeah, we have not thought about the bulk interpretation. For this, so actually we do not know. So we have not studied that area yet. So
okay.
We will do it in the future.
Just to add to that, if you take, for example, instead of Einstein gravity, if you take, let's say, WW tilde, okay, in the bulk, that will actually produce a parity-odd non-homogeneous term, but that turns out to be a contact term, okay? That actually, you can show that in general for arbitrary spin, you can define one mode structure, which is always a parity-odd contact term. What we are talking about here is a non-homogeneous parity-odd, which is not a contact term, and but it has some peculiar property. As Abhishek said, we have not thought about in the gravity. We are not sure how to get them in the gravity. Okay.
Right. Okay. Thank you.
All right, Alok, you have a question?
Hi, Abhishek. Yeah, just a small question. So the double copy, I mean, usually in the amplitude case, we see that there is a double copy possible when the
gauge theory amplitudes, have a BCJ relation, right? I mean, we can't write if we write the gauge theory amplitudes in some Feynman diagrams, then the double copy is not manifest. So here, is there because you didn't show the color factors, I mean, is there a BCJ relation in your current correlators that allows you to do the double copy? I mean,
actually, we have not looked into that.
I see. Okay. But it could, yeah, I mean, there are some color factors that you didn't show, right? Yeah.
Right. That is right.
But you're saying it's not clear if the BCJ relations are satisfied for this current correlator.
Yeah, we did not look into it. So we're not sure.
Yeah. I just want one more small question that I know you said you did not look in the bulk, but there was a paper recently by Radu and others where they look at the bulk ADS amplitudes, tree level, and show that there is a double copy from Yang-Mills to gravity just by looking at the bulk ADS amplitudes using Witten diagrams type.
You mean for the correlators?
Yeah, exactly.
I see.
So I mean, I don't know if this is related to you have a
no, I have to see. I will see and have a look into that.
Sorry, Alok, was it 4-point function or 3-point?
Yeah, 4 point. Yeah.
Yeah. So Alok, so right now we are just this is actually at the level of 3-point function, and
yeah. So there it is certainly easier for them. I mean, they went beyond. So certainly
at
3-point
level. Yeah.
Tree level. Yeah.
Yeah. So actually, one of the aim is to we understand this 3-point structure really well now. One of the things you can show that just imposing the double copy has to persist at the CFT-Coulter level. You can actually see that only free theory, arbitrary OP coefficient, only free theories has this kind of double copy structure. Of course, not the structure with the OP coefficient I'm talking about. So one of the aim actually is to just see in 4-point function in general what one can say. Yeah.
Okay. Thank you. Thanks.
All right. Any other quick question or comments? Okay. If not, let's thank Abhishek again for a very nice talk. So our next speaker is Arnab Kundu. Arnab, you're here.
Yes. Can you hear me?
Would you kindly share your slides?
Yeah. Actually, Abhishek has to first answer.
Oh yeah, sorry.
Oh, okay. Yes.
Yeah.
Okay. Yeah. Is it visible?
Yes, it is visible.
Okay, and you can hear me also.
Yeah, so our next speaker is Arnab Kundu from Shah Institute, and he'll be telling us about OTOCs and early time chaos.
Okay, thank you. And I have about 25 minutes, right?
You have 25 minutes, and then we'll have 5 minutes of questions.
Okay, thank you. So let me begin by thanking the organizers, especially Alok, for organizing this wonderful conference. It would be very nice to meet in person, but at this time, this is also great. So what I will try to talk about is actually some sort of elaborate version of what Srichetan talked about this morning. But I will try to actually focus on a little more broader aspects and probably try to impress on you what it is that that we are trying to do in the longer term. So, and in doing so, it would be mostly, or at least a large part of it would be reviewing or introducing, discussing very elementary things that I apologize if you are way too familiar with. But I hope it's not going to be boring or useless. Okay, great. So with that apology, let me start. Great. Okay. So first, I should acknowledge really great people that I have been fortunate enough to work with. And what I will be talking here today is largely based on the first two papers here with Srichetan, Bobby, Somnath, and Vaishali. And then finally, we had we also had the great fortune of Krishnan joining us from a very different perspective, more from a condensed matter kind of perspective, in essentially trying to do some computations that we are currently figuring out, and it's great because it's a new perspective, but it's also at the end of the day doing the same or similar calculations in a more in a wider sort of framework, and trying to ask physics questions. So that's great. And Srichetan already talked about it today, so I'll not really be talking about the results that we have there. I will mostly talk about some results that we have in these two works, and how it tries to connect to the bigger picture and so on and so forth. Okay, so this is the rough outline. So I'll start with a brief motivation and some introductory remarks. In particular, I'll try to basically say that I'll try to impress on you that dynamics is an important aspect to think about in physics in general, no matter what kind of questions you are interested in at the end of the day. And if you want to understand dynamics, it's a very difficult problem at the same time. So one has to have a starting point. And in particular, for this talk, I have chosen this class of correlators, which are abbreviated as OTOCs these days. And basically, that's what I will introduce. And in particular, more than introducing them, perhaps more important is that I'll try to also state that, or rather make a statement, how it connects to various other interesting ideas and perspectives in physics that people are using, including efforts of experimentalists that are going on currently. So that I find is extremely exciting, this is perhaps a good point to try to think about this class of correlators in general, in any theory that you like. And then with this sort of broad discussion or motivation, I will try to move on to a particularly precise setup, which is, I'll try to talk about quench and chaos. And this will also have a very precise meaning. I'll obviously not be talking about the most general kind of quench that you can think about or that you can do. In fact, here we will take literally baby steps to something that are the simplest in some sense. And here the point would be that in the simplest cases, nonetheless, what you get at least seem interesting to us for a variety of reasons. So that would be my purpose to establish at this point. Of course, general notion is that here, in some sense, we are probing non-equilibrium physics, but of course, it's not the non-equilibrium physics of an arbitrary nature. It's a very specific kind of non-equilibrium dynamics, but nevertheless, it has structures. And then I will try to go on to some specific, what I call some specific but general lessons. I hope you will appreciate this phrasing once we get there. This is where most of the discussion of results will take place. And then I'll try to conclude with some speculative remarks, perhaps some definitive follow-ups that one can do, and so on. Great. So let me start with perhaps the broadest possible perspective, which is to say that dynamical aspects are undoubtedly ubiquitous in nature. There's no doubt about that. And if you want to do a collider experiment or a tabletop experiment or a cosmological experiment or what have you, you will have to address dynamical aspects in one way or another. As ubiquitous as these aspects are, they are also very difficult in general, that I don't think anybody will disagree with. So if we want to understand dynamics properly, it is a seriously challenging problem in general. In particular, perhaps to this audience, I could appeal to particular corners of this dynamical problems. For example, if you want to understand dynamics for strongly coupled quantum field theories in general, or in particular, for example, quantum dynamics of black holes in quantum gravity. I think at some point these questions will need addressing anyways. So these are going to be these are already challenging, and I'm just trying to say that these are important problems to understand in general. But of course, every challenging problem has its problem in the beginning. Where do you really begin? And one particularly interesting beginning point is perhaps to look at correlation functions, and that has been happening for decades. In fact, it goes back all the way to, I think it's fair to say that understanding correlators and their analytic structures, etc., is one way of understanding traditional critical exponents, universality, and so on and so forth in a quantum field theory setup, for example, that we cherish now. However, those are only a handful of examples in some sense. And I think it's also fair to say that there is no structured, systematic understanding of correlators and their analytic properties or the power of it in full generality. There certainly isn't, although there are many structures which you can explore. And in fact, in some sense, recent years have seen such a push, for example, to understand analytic constraints on correlators, in particular, these class of out-of-time ordered correlators that I'll be talking about. So two examples I'll give you is, well, the well-known 𝗕𝗵𝗶𝗁, for example, is a precise example of this, where analytic constraints does put a bound on the correlator or how it behaves. In fact, I'll also allude to 𝗕𝗵𝗶𝗿's talk later in this conference, where I think he'll be talking about a much more general class of constraints that one can get with similar analytic completion arguments, for example. So the point is that this, I think, broadly speaking, is a very important problem and a very interesting problem nonetheless. And there are lots of things to do. However, the trouble is, or the challenge is, in some sense, is that it's not clear immediately how these constraints or how much these constraints on correlators could give us control over a system, for example. So one can start from that. One can start from an abstract point of view like that. Instead of doing this, the point of view that I will be adapting in this talk is mostly like a crimes in investigation, where someone just basically collects evidences, and it's going to be somewhat messy. But before we warrant or issue a warrant, that's the way we want to proceed, at least for the time being. So that would be the approach. Okay. So let me start with this notion of OTOCs, and I apologize if this is very, because this is very elementary, but I'll go through it very quickly. So as we all know, that classical dynamics, in classical dynamics, the notion of chaos is very important, and it is defined in terms of trajectories, classical trajectories. In particular, as the picture shows here, I hope you can see my cursor. If you have two nearby trajectories at initial point, if you have a highly sensitive system, a dynamical system which is highly sensitive to initial conditions at later times, at sufficiently later times, these trajectories will start deviating from each other by a large amount. In particular, this is a very functional quantitative way of estimating how these two trajectories could be differing from each other. And in particular, they could be exponentially growing in time. And the exponent of that has a name. It's basically one of the important ingredients in this part. It's called this Lyapunov exponent. So that's the classical part. And basically, the bottom line is, if I know the phase space, if I know the phase space structure, if I know my Poisson brackets and so on and so forth, I can compute this for a particular system. Great. So once we go to quantum mechanics, of course, trajectories go out of the window, but what we have is still the correspondence principle in a semi-classical regime. So what we do is we take the commutators, we take the Poisson brackets and lift it to commutators. That's the correspondence principle. And generally, what you can define is a quantity like this, which I call Cn of t. So basically, this is just as you can see, just a commutator raised to some power, where the commutator is between two operators. One is evaluated at a time t, and the other one is evaluated at 0. T and 0 has really no meaning. It's just to emphasize that you could put it at two different times. I'm suppressing the spatial direction altogether. It's not going to be important. And you could do this computation in fact in any state. Although I have written here, there is a subscript beta here because generally thermal states or thermal-like states are the ones we want to consider in these cases. But you don't have to. I mean, this is just a set of correlators. In fact, this can define a sequence of correlators depending as indexed by n, for example, for any gauge invariant observables that you have, local observables that you have in your theory. In particular, if you take n equal to 2, you can expand this out. And if you expand this out, it will have two pieces. One is the standard time-ordered correlator that we are very familiar with. The other one, which we may not be so familiar with, are these out-of-time ordered correlators. And as the visual cue suggests, basically, as you can see, that the operators have time arguments which are alternating here in the out-of-time ordered correlators. So that's all really really all that there is to it. From a pragmatic point of view. So these are the correlators, if you wish, that I want to talk about a bit more. Okay, sorry, I went too fast. Okay, good. So what is the physics of such correlators? Well, So as I said, these questions pertains to dynamical questions. So we are trying to understand dynamics. And if you want to understand quantum dynamics, you can already organize your question in various time scales. So for example, here is a cartoon of this. So this horizontal line here, horizontal arrow here, denotes basically ascending time scale for a quantum mechanical system. It could be quantum field theory, it could be anything that you like, but it's quantum mechanical. And there is an very early time, which I call T dissipation. It really doesn't necessarily have anything to do with the dissipative thermal physics, but it's similar. The point is that this time scale is given by order S to the 0. So this is order 1, if you wish, as far as entropy is concerned. And then there's a time scale I call T scrambling, or rather it's known as T scrambling, which goes as logarithmic of S. And then there's a very large time scale, which is known as the Heisenberg time scale, which grows exponentially with the entropy. So for all the discussions that we have, or for most of the OTOC discussions that take place in the literature, the entire non-trivialities are happening around this time. So you can think of it as a physics which is happening near the scrambling time. And that's what I will call early time, just because in the literature, late time chaos means something else in quantum dynamics, and that has to do with this physics at the Heisenberg time, which I'll not talk about. So everything that I have to say here will actually be strictly limited to the scrambling time region, and certainly not for parametrically larger time scales. So what is the physical content of such correlators? Well, some very simple things that come out of these correlators are basically an emergent light cone. In other words, if you compute correlators, correlation functions, for example, even a 2-point function, in a quantum mechanical system, you do see an emergent light cone, in the sense that the correlator is order 1 inside and vanishingly small outside, exponentially small outside, and so on and so forth. So this light cone structure is what comes out of OTOCs cleanly. Of course, this Lyapunov exponent that I just mentioned in a slide back, and also something called butterfly velocity, which basically defines the light cone. So all these data are essentially just defining an effective or emergent light cone. If you like, this is basically like the Lieb-Robinson kind of light cone. Now, I just want to mention a couple of lines here. I mean, I'm of course not an expert in this, but I think it is rather interesting that right now this class of correlators are actually connecting many ideas, starting from dynamics of black holes to, for example, actual measurements with cold atoms and so on. And also connecting connecting also ideas of operator growths, quantum information theoretic quantities, and so on and so forth. In particular, I just listed a few very representative experimental efforts or connections that are going on right now. So just to sort of impress on you that this is not completely an abstract thing. This is actually something that people can measure in the lab right now. That much precision they have. So how do we compute such objects? Well, in a field theory, if you give me a field theory, there are certain approaches, but there is no really extensive or exhaustive set of techniques that exist right now. So for example, what I will be considering or focusing on is basically just Euclidean computations, perhaps the simplest of them, because I'm going to choose conformal field theories, and then some analytic continuation accordingly. But there are other techniques, for example, large and diagrammatic. If you are powerful enough or motivated enough, you can do that. And then there are some very interesting papers by these people recently where they are trying to use a mean field type description to compute such correlators. But I will have nothing to say about that, at least today. Okay, so some very basic details. So as we all know very well, that if you want to compute a vacuum correlator in a Lorentzian quantum field theory by analytic continuation, what we do is very simply compute the following. So these T's, for example, this is the Lorentzian correlator. What you do is you take your time coordinate and make it analytically continue it, such that if all phi's are Heisenberg operators, you can show that this correlator is nothing but what I have written here on the right hand side. And of course, at the end of the day, you take all the epsilons going to 0. But in doing that, what you ensure is, because of these time differences, these tau 1, 2s, and so on and so forth, it introduces a set of regulators In this case, it will have a set of 3 regulators because I have chosen 4 fields, but in general, you could do it generally, of course. And this set of regulators have to be properly sequenced with an order so that the entire right-hand side is well defined, in the sense that all of these regulators have to be damped, right? I mean, it cannot grow. If it grows, then the right-hand side is not well defined. So in order to well define this object, it all automatically gives you an ordering of this epsilon, and by definition, that orders your operators. So this is a simple way of understanding how vacuum correlators in Lorentzian QFT are ordered. Of course, if you want an arbitrary state, which is what we actually want generally, then this trick will not work. But what will work is the following: that if you start with the general state psi, which may not be a normalizable state, what you do is you just introduce by hand a regulator where this tau naught is a parameter that needs to be identified with some physical parameter that is in the system. But nonetheless, you can do it. And when you do it, because of this damping or because of this regulation, your correlation function is well defined. So here in the violet box, I have shown 2 examples. For example, this one where phi1, phi2, phi3 are time ordered. And that happens if you choose a sequence of epsilons in this way, for example. On the other hand, if you choose a sequence of epsilon where this epsilon1 and epsilon2 are switched, then you find an operator ordering, which is where phi2 and phi1 are also switched. And note that this is a correlator which is being computed in a non-trivial state or in an arbitrary state, psi, not necessarily a vacuum state. And because you are computing this correlator in an arbitrary state psi, even 3-point functions are non-trivial. So generally we talk about 4-point functions when we talk about non-trivial time ordering and so on and so forth, but that's not necessarily true for an arbitrary state. Okay, so that's the very basic premise. Now let me come to the quench part, or let me just introduce what it is. It's a very basic thing. Quench is essentially a quantum mechanical process where you change the Hamiltonian in time. In particular, this picture basically gives you an idea of what is happening. So for example, you start with a Hamiltonian H1, and then, well, that remains for a while. Then suddenly at some point, you change the Hamiltonian to H2, which is a completely different Hamiltonian. And this change can be very slow, which is called an adiabatic quench, or it can be extremely fast, which is usually known as abrupt quench. So if it is abrupt, if it is extremely fast, which is the case that I will be, in fact, that I will be talking about, I will not be talking about at all the adiabatic part, although that is also very interesting. So then what happens is essentially you start with the state here, which is, for example, say the ground state of this Hamiltonian H1. But on the right-hand side, you evolve this state, which was a ground state of H1, but with the Hamiltonian H2. So this, of course, this psi is no longer a ground state of this H2. In fact, this is the way you will create an excited state for H2 altogether at late times. But this is generally the setup, and the kind of questions you ask or the quantities that you want to compute are basically correlation functions in this state as it evolves in time. So this is completely I'm completely choosing a Heisenberg, working in a Heisenberg picture here. In particular, there are 2 classes of physics questions that one can ask. One is basically the physics of thermalization. And the other one is essentially physics of universality. If, for example, you choose this H2 to be a CFT Hamiltonian. So in particular, if you quench with a CFT Hamiltonian, then you would expect, because of CFT, because of that symmetry, you will have many universal features surviving at long time limits, and indeed that happens. So these are the two kinds of broad questions that you can focus on with this setup. So here, of course, I'm going to consider a critical quench, and in this setup, talk about OTOCs and its physics. Okay, so for example, a very basic example of universality is if you just compute 1-point function, you can define a relaxation time scale, and if you take ratio of 2 relaxation time scales of corresponding to 2 different operators, it's just a ratio of their dimensions. So that's an universality. From a 2-point function also, you can define an universality, and you can get what you get out of it is an effective temperature that comes out. That has been discussed in detail by Ghadi and Calabresi over the years, for example. But what is peculiar here is that these universalities do not really care about what CFT you chose. For example, you could have chosen a minimal model, or you could have chosen a large C holographic CFT. These statements are nonetheless true. So these correlators are obviously not capturing the fine-grained information, and that's not completely surprising. But what could capture the fine-grained information, for example, higher point correlators, which is what we are after with these OTOCs. So let's see what comes out of it. Before that, let me just very quickly describe what goes on. Well, as I said, that if you want to compute the correlator, you have to, first of all, compute in an arbitrary state. You have to do this regularization. And that regularization essentially means for CFT that you're computing a correlation function inside a strip with operators located in this, operators arranged in this manner, for example. And you can make a standard conformal map from a strip geometry to the upper half plane. And basically what will happen is that this W will have an image, and the 3-point function will now become a holomorphic part of a 4-point function, which you now have to evaluate. And this spatial operator arrangement is useful or very important because of the following reason. Because what we want to do is the following, or what you want to capture is the following: that the 4-point function, which is a function of the cross ratio, should have the following feature, that the cross ratio should have certain kinematics. In particular, as t goes to 0, at small times it should go to 0, as well as for large times, which is these two limits, for example. And as t is equal to x, which in that picture is basically the operators entering each other's light cone, it should become bigger than 1, because then what will happen is in the plane, the cross ratio will actually cross the branch cut and go to the second Riemann sheet. This is important for OTOCs. If this is not bigger than 1, then you do not get a out of time ordering. You then get a time ordering, in fact. So this is what is ensured by ordering the epsilons, as was described by, demonstrated by Roberts and Stanford some time back. The point is that you can do this with 3-point function also, which is what we had done. Good. So what comes out of this calculation is the following. So you take, first of all, the simplest example that we all know and love is the large CFT. We know it's chaotic, we know it's holographic, and all those nice features are there. If we now implement all of this prescription, it's just a black box. You just have to do it, and you will find a set of interesting answers, and that's the following. So this f of t is the OTOC, and it has this structure. So as you can see that it grows exponentially in time up to t star, and this lambda L is given by essentially 2 pi times t effective, where this t effective was again the same t effective that we read off from the lower point functions. So lower point functions told us that this Kārdi-Calabresi states or Quench actually looks like effectively thermal, and it is indeed so for large CFTs. In fact, you can also argue it is maximally chaotic in the sense that it saturates an analog of the chaos bound, for example. And more importantly, again, what you have here is a scrambling time, which goes as log C, and this scrambling time is what separates these time scales between tau 0 and t star. So tau 0 sets a time scale and t star sets a time scale, and they are far apart, where you actually do see this non-trivial evolution happening. So I should point out that, of course, this calculation you could also do in minimal model, or you could do in other CFTs, for example, an orbifold CFT, where you get a very different result. For minimal model, you don't get any evolution at all at late times. It's just a constant, completely trivial in that sense, which basically says that it's a highly integrable model. You can't really do much. You can't really create much chaos, quote unquote, into it. On the other hand, for orbifold CFTs, it nonetheless exhibits a power law growth in time. However, a power law growth is not really enough to give you a scrambling time because it doesn't really define a scale. So there is no notion of scrambling time, so to speak, for this case. Good. So let me just collect the circumstantial evidence again.
Sorry to interrupt.
Yes.
You should try to wrap up within 5 minutes, including questions.
Yes, I will. Yes, I will. Good. So, so first of all, based on the large CFTs, you can already make a statement that the Lyapunov exponent is actually bounded by the mass gap, the initial mass gap that you chose, this tau naught, the scale that was set by tau naught. And this can be further argued based on the fact that this 3-point function that we started with or we discussed actually does satisfy all the assumptions that goes into MSS bound proof, for example. So you would expect that this would hold up. On the other hand, there are very interesting explicit examples or explicit cases worked out, which are non-critical quenches by these people here, which actually does obey this bound. So there is some concrete evidence to trust on or to think that there is indeed a bound. However, there's an interesting thing that you can already observe, which is the Kārdi-Calabresi state is a very special state. In that, it's not actually an eigenstate of the CFT Hamiltonian. In fact, it is not really a typical state at all. It's usually dubbed as an atypical state because it's very special. So we do not quite have the CFT arguments that go along the lines of typicality, that if you have a heavy state in CFT, it does behave like a thermal state. That is not necessarily true here. So in that sense, it's peculiar as well as interesting. So with that, I'll very quickly in the next couple of minutes tell you that what I have been saying so far, you could also very easily do with some inhomogeneity. And well, inhomogeneity can be, of course, motivated on many grounds. I mean, if you want to connect things to the real world, as well as perhaps even formally, it's not such a bad thing to think about, especially now when people are thinking about quantum field theory with lesser and lesser amount of symmetries, for example. So anyways, that's just a side remark. But the point here is that even with inhomogeneity, if it's small enough, there is already a technology that exists that will tell you, in other words, a set of maps that will tell you how to go from basically the inhomogeneity that is described here by a wiggle line to the upper half plane and carry out this exercise, which you can, which we did. And what you find is the following. You can, of course, follow your nose, etc. But roughly speaking, a structure like this comes out. And here, as you can see, that inhomogeneity is a perturbative parameter here. It's by definition perturbative. This entire premise is perturbative. So we cannot trust it when the inhomogeneity is large. But nonetheless, what happens is the structure becomes like this. So you have first for the standard Lyapunov growth that exists for the homogeneous quench. But on top of that, now you have also some other exponential piece. And later in the conference, I hope 𝗤𝗵𝗶𝗿 will tell you that there are actually an infinite number of constraints that you can have on such behaviors. And all I want to say here is that by choosing an appropriate inhomogeneity, you can indeed saturate one of the bounds that he seems to be getting. So that's an interesting observation. I don't really have anything profound to say about it at this point. So finally, last point is the following. I said that the orbifold CFT has a polynomial, has a power law growth, not an exponential growth. So it did not have a scrambling time. But if you have a small inhomogeneity, it's a small parameter in the system. And the point is that if you just carry out your calculation, what you find is that that small parameter goes into define for you a scrambling time right away in the otherwise system which did not have a scrambling time. So all I'm saying is that this is non-trivial because you might think that a weakly coupled system would also be able to do that, but it's not known to be so. Usually, hierarchy in scrambling and any other earlier time scales is given by a large number of degrees of freedom. But at least in these cases, within the approximations, etc., we are working in, you can indeed create you can indeed zoom into the chaotic region if you wish. And perhaps this could be relevant for experimental protocols and so on. Also, I do not have anything more precise to say about experiments here, but just an interesting observation. So let me end here. As I hopefully try to convince you that this set of correlators are important as well as largely unexplored because they are hard to compute. Of course, they contain finer grained dynamical information. That's not surprising, but the question is how much? That's a hard question to answer. And of course, these correlators actually involve what I call commutator class operators. Basically, any operator that you can define as commutators or nested commutators of local operators. And these class of operators encode very, very interesting information about the quantum mechanical system. For example, how fast a local operator grows and so on and so forth. Information spreading in general. Of course, there are also traditional quantum field theoretic questions like how it knows about critical exponents, RG flows, and so on and so forth. Also, there are statistical mechanical perspectives or questions that one can ask. To what extent you can actually distinguish between typical and atypical states of a Hilbert space by these correlation functions. I think these questions are relevant for quantum field theory as well as holography, and generally ties with this analytic, how much analyticity can constrain, etc., etc., etc. So with that, I will just end by saying that, well, as I started by saying that, we're doing crimes in investigations, they are underway, and hopefully in due course, we'll be able to produce clean warrants, exhibits, and legal documents. So thank you for your attention.
Thank you, Arnab, for a very nice talk. Any quick questions or comments? I mean, we don't really have a time for that, but any quick, yes. So yes, 𝗤𝗵𝗶𝗿, there's one question. Yes.
Yeah, thank you for the nice talk. Just one question regarding the last part of the talk that you said. So, like introducing a small homogeneity, you said like in systems where you had like power law growth and where you couldn't define the scrambling time, introducing a small inhomogeneity allowed you to do so.
Yeah.
Can one think of it this physically, that this introducing this inhomogeneity somehow breaks the integrability, and from that can one argue that there should be?
Yes, that is certainly true. I would agree with that. But the point is that
this true in general or
carefully. Yes.
Yeah, I'm asking. I'm asking that whether this is true in general or is it like true?
I don't think it's known. So, for example, if you take a sufficiently integrable system, classical mechanics, your 𝗕𝗵 theorem tells you that by perturbation you can't break integrability.
Right.
So, in some sense, the fact that minimal models don't really respect these OTOCs they don't show respectable behavior or they don't care about them, it's sort of a manifestation of that. What remained without the perturbation also remains true with the perturbation.
Okay.
So if it's sufficiently integrable, no, but yeah, otherwise it might.
Okay. Thank you.
All right. Thanks a lot again, Arnab, for a very nice talk. We'll move to our next speaker. So our next speaker is Ayan Mukhopadhyay. So Ayan, are you here?
Yes.
Yes. Would you please share your slides?
Are they visible?
Yes, they are visible. Yes. All right. So as I said, our next speaker is Ayan Mukhopadhyay from IIT Chennai, and he's going to tell us about quantum thermodynamics, erasure, entanglement, and holography. Yes.
Okay, thank you for this introduction, and I'm very, very happy and very grateful to get this opportunity to give this talk in this in the international version of this Indian string meeting. So my talk will be already, the title has been announced and it is here. So what I will do, I will first start by explaining these two words, quantum thermodynamics and erasure, which may not be so familiar to all. And before going there, this talk is based on this paper that we recently had, a very recently started program. Although we started working on it a little bit earlier, but we started understanding better what we are doing only recently, and we have this paper out now on the archive, and there's one coming very soon, hopefully this month itself. And there are actually many upcoming works which are coming on. I mean, we have already results which are going to be published with many other collaborators also. And I'm very thankful to have a very good postdoc, Pratik, and very good student, Tanay, who has done much of this work for this project. So, okay, so let me give some idea about what I'm going to talk about, this field of quantum thermodynamics. So to introduce these ideas, let us take some two simple questions that one can ask for a finite dimensional quantum system. The first question is, what is the minimum cost of preparation of a given mixed state? I give you a mixed state, and how much minimum cost, what cost in a single shot, means in a single operation, that you have a single operation to prepare the state, and what's the minimum work that you require to do it. And also you can ask a similar kind of question, what's the minimum work that can extract it from the state? For example, you can make the state go to another state and in this process extract work. So how much is the maximal thing that you can do? And of course, here this assumes such an Hamiltonian and such an thing. So basically, the answer to this process, answer to both questions were given by Junger Halpern, and Joseph Rennes in 2016 in a remarkable paper. And what they were able to show that for a single shot process, in one shot process, the answer to both questions are in a quantity called hypothesis testing relative entropy. You might know relative entropy, but hypothesis testing relative entropy is a certain version of that, where you have only one copy of the state and not several copies. And this relative entropy is between the state that we are talking about and a suitable Gibbs ensemble, a thermal state, is determined by the energy. This hypothesis, and of course, it's an epsilon approximation because you can only prepare a state within an epsilon approximation. So this epsilon approximation included in this definition of hypothesis testing relative entropy. So these are gives the bound. So this is a very simple. This comes from quantum information theory. More generally, you can ask the question: how much resource a quantum channel needs, because resource is not only energy, but also other things. For example, entanglement. For example, if you have to work a teleportational quantum channel, it requires non-local entanglement. So the question is how much non-local entanglement you need, or if you need energy, what is the energy cost for operating the channel? And similarly, you can ask what is the maximum rate of a catalytic reaction. You can ask what is the maximum energy efficiency of a quantum engine. Now, this is also different for a quantum case because, for example, if you have just isolated hot and cold system in contact with each other, heat can flow only from the hot to cold. But in quantum, if you allow entanglement, initial entanglement between the hot and cold bodies, and they're isolated from rest of the universe, heat can still flow in the other way without violating second law because entanglement entropy takes care of it. So you see that you need many other resources, not only energy, but also entanglement. And you can ask, what are these kind of resources needed to operate a quantum engine? How much of heat supply, how much of entanglement supply you need? And similarly, if an irreversible logical operation, this is a sort of Landau erasure constraint. If you have irreversible logical operation in a quantum computer, is there also an irreversible thermodynamic cost? And so these are the very general set of questions. It was very nice review by 𝗲𝗵𝗿 and Gaur in 2019 review of Modern Physics volume. So you could look up there, and then most of these questions are known in the context of finite dimensional systems. So not much about many body systems. So here holography is promising because firstly you might think that in large N limit, the answer to these questions might be simple for whatever reasons, because large N things do simplify to some extent. But there is also opportunity in holography because there are these prescriptions to compute entanglement entropy. There are now even prescriptions to compute entanglement negativity. And also we know that modular Hamiltonian or slightly excited states, slightly excited from vacuum, are related to canonical energy, at least if you take ball-shaped region. So you can also compute relative entropy. So there are some things that we know how to compute in holography. And holography also provides an independent additional motivation, which is as follows, that quantum engines can be also made out of evaporating black holes. So you could form a black hole, make it evaporate by changing boundary conditions. You can make it either completely transparent, or you could make it absorbing, or reflecting, sorry. So you could do all of that. And so there is, so I will, at the end of the talk, I might have a few more things to say. There's an intimate connection now between quantum thermodynamics and quantum information aspects of gravity, with profound implication for the information paradoxes. So that gives you an additional motivation to also do these questions. So what we will do, we will try to look at one such set of questions in this talk and what we have been able to answer and the method. So what is the simplest question that you can ask in this context? So for good reasons, we would take a 2D holographic system and not, it is much easier to answer this question because, as we will see, easier to compute entanglement and the other stuff that we need. So this you connect it to an infinite energy memoryless bath. It's a typical simplest setup. It's a bath that has infinite energy and has no memory. And you start with a quantum equilibrium state. This is analogous to the generalized Gibbs ensemble. Essentially, these are like Virasoro hair on top of a thermal state or a vacuum. And then what we do is we let energy and momentum flow from the bath to the CFT. So what happens is that your one quantum equilibrium state goes to another quantum equilibrium state. So what we ask is the following question. So suppose a given Quench protocol, suppose we think of a Quench protocol that drives such a transition. You start with one quantum equilibrium state, we go to another. Is this physically possible? So is there a physical process that can be applied by changing the couplings of the theory or driving some Quench such that you can go from state A to state B? And this is a question that's already relevant for cold atomic gases trapped in a laser. So you could think in a laser, laser can be thought of as an infinite dimensional. It's a 3D thing and a 2D thing, lattice on top of it. So it's like a laser is practically would be an infinite dimensional, but if not, and in some approximation, it is memoryless, say, and then you could ask that I change properties of the laser that change properties of the couplings between the atoms, and I can drive a Quench, and therefore I can inject energy and momentum that allows this transition from state A to state B possible. Now, classical thermodynamics will simply tell us that for an infinite bath, that your entropy and temperature must always increase in the system. And this is also obvious in classical gravity. If you have a classical gravity with Dirichlet boundary conditions, nothing dynamical in the boundary, or even then the entropy will always increase. And so this is the entropy has to increase monotonically, even for other boundary conditions. And quantum thermodynamics will tell us that that indeed, I mean, that in all known, as in finite dimensional cases, it will not violate classical thermodynamics, but it will tell you that often what we think in classical thermodynamics is sufficient is insufficient. You need more constraints. So for one of the surprising results we will see that if you increase the temperature by such an amount, then there is both a lower bound and an upper bound to how much the entropy can increase, which is surprising because classical thermodynamics will simply tell you both will increase, but their lower bound is surprising and upper bound is also surprising, equally surprising. So these are the things that we will see soon. This is simply examples of it, but these kind of questions also incorporate erasure, because when you go from one state to another, you could think of going from a inhomogeneous state to a homogeneous thermal state. So that would be like erasing information. So it's already, so all of these things are included in this very general class of question. So all this is a simple question, but it already involves many non-trivial protocols. And the simplest tool that we can use to analyze whether such a process is possible or not possible is the quantum null energy condition. I don't have too much time to elaborate, but originally it was proposed by 𝗏𝘃, 𝗏𝘃𝗀 in 2016, based on the quantum version of the Ricciother equation. So there naturally this generalized entropy came up, and then you can take the limit where gravity is switched off, and then you get a condition with pure quantum field theory without gravity. And this condition turns out to be that the expectation value of the energy momentum tensor is essentially greater than the second derivative of the entanglement entropy. Now in 2D CFTs, this precise statement was first made here, where this inequality can actually become an equality also. And then it was proved rigorously in 2D CFTs generally by Srivatsan, Faulkner, Thankar, Wang. And of course, there are many, many other works where this has been proved in different other contexts. And so there's a double, you can get a list in a paper. So essentially what is the statement is that you take an interval where you are, and this is your point of observation where you are measuring these non-vanishing components of the energy momentum tensor, which are T++ or T-. And then you take any interval that ends at this point and you deform the endpoint in dx plus or dx minus direction, and you compute the variation of the entanglement entropy and you do this deformation. So that defines the right-hand side, these two terms. And this has to be, this minus this has to be greater than or equal to 0. And any state or any theory, any geometry in the bulk which will violate this condition cannot be physical, it can relate to a physical state. Okay, so this is now we come to the setup. So we have to investigate these classes of questions. We have to consider some very general geometries that does such transitions between quantum equilibrium states. And this is the most general answers that you can take. So M is a function of T and X, J is a function of T and X. And now we want these to satisfy Einstein's equations, which are of this form. Now here is something that we will do, is that what we want to go from one quantum equilibrium state to another quantum equilibrium state, and these will be essentially general. Each one will be a Barnard's geometry on its own. So this is what is well known, and that actually tells you what kind of TMN you can take at all, if any kind of TMN. And so we will be completely agnostic about what is the content of the TMN, right? So we don't know what bulk matter it is made of, because we can do a very general analysis. We don't care about it. But of course, this TMN has to be conserved in this metric, whatever TMN we will take, and will provide the right Israel junction conditions that can give you a transition from one Barnard's geometry, any arbitrary Barnard's geometry, to any other arbitrary Barnard's geometry. So if you allow such the most general such class of states, TMN would be of this form, which is conserved in this metric without applying anything else. Now, the Einstein's equations will simply reduce to these two equations, constraint equation, rather simple. So actually, you can easily see if I put this P and Q, which determines this energy momentum tensor completely, to 0, the most general solution are of this chiral form. And these are essentially the Barnard's geometries, where this M and J takes these chiral forms. And the one good reason to call them quantum equilibrium states is that these inequalities are completely saturated in this equals to 0. And this was actually first shown by Daniel Grumino and Christian and Shaheen in a paper, 𝗍𝗃𝗃𝗃. So I'm sorry I didn't put this reference in this year. I should have. So these these inequalities are saturated in all of these quantum equilibrium states. And these are essentially Virasoro-Hare on vacuum or thermal states, but some of them are much more exotic because you have to use this co-adjoint orbits or Virasoro group. So I don't have time to explain the whole class of such states, but for the moment, this is good enough for us. Now, if you have to drive some instantaneous quenches between two things, you have to simply M of this form. So for t less than 0, you have one quantum equilibrium state, while L plus and L minus are given by this I's. And for t greater than 0, you have two other class of quantum equilibrium states, where this L plus L minus given by this F's. So you have 4 functions, one for t less than 0, and one each for the chiral component, not for the anti-chiral component. And yeah, so you have 4 such functions. And then P and Q are then delta function like. So basically it's a null shell that is following in, but it's an inhomogeneous null shell where P and Q are given by this solving this equations is rather trivial. It will be simply given by delta functions and the differences of this L plus and L minus. And if you do holographic renormalization here, the boundary state is the boundary T plus minus that. So this is the thing that appears here, which is of interest. So that would be simply one quantum equilibrium state before t less than 0, and another quantum equilibrium state for t greater than 0. So that's rather simple. So that is exactly what you see with a factor of c by 12 pi, which is well known. And these states satisfy these word identities where del mu t mu is equal to this, where f nu is simply is q and p, these delta functions. So basically, this is q is the heat injection and p is the momentum injection, both of which are inhomogeneous, in order that this can happen, this transition can happen. So this is basically the simple gravitational description of such states, where you are completely, you don't ignore, you can completely be ambivalent about what makes up the bulk French tensor. But anyway, when the quantum null energy condition is satisfied, we also find that this bulk matter satisfies classical null energy conditions. So this is sort of usual classical bulk matter you need. You do not need exotic ones to make it happen. Okay, so now we have found out this method, cut and glue, in order to analyze such things. So this method tells you how to compute the entanglement entropy and how to compute its time derivative. And it goes like this. So what you do is that you know that before t less than 0, you have a Barnard's geometry. After t greater than 0, you have another Barnard's geometry. You can do uniformization maps, which we found out first, I think, in the Eddington-Finkelstein coordinates. So these are completely well known. We have completely found it out, not yet exact ones. So that you can use to go to Poincare coordinates, but there are 2 different Poincare coordinates. Now, when you do that, so your gluing surface is simply t is equal to 0 in the physical coordinates. That gets 2 images, one here and other here. So you have to go from one image to the another, and that can be simply gone by requiring continuity of the physical coordinates r and x. So if you just simply do that, you can know which point here to identify with which point on this surface. And then the geodesics are trivial because geodesics are simply semicircles. And now we have also a continuous version of this, which can not only handle instantaneous quenches, but also can handle smooth or other time varying things. As long as you keep geometries of this kind, we would be able to handle these kind of analytic methods now. So therefore we can compute many things analytically. So all the results are analytical. Of course, sometimes we do semi-analytic because the expressions are often like extremely long and we cannot simplify, and then you can only plot them. But otherwise, where we can simplify, we have been able to simplify, and our results are all analytic. So let's see what QNEC allows. And the first type of question you could say that let's just look at initial and final geometry as simply BTZ black holes. So you have T++ and T minus, both to be constant. There's mu plus and mu minus. So mu plus is the right moving temperature, mu minus is the left moving temperature. The Hawking temperature is a geometric mean roughly, and the entropy density is simply the sum of mu plus and mu minus. So this is how we describe the initial and final states. And then you can see what QNEC is allowing. So first of all, the strictest conditions of the quantum null energy condition only comes from very, very large lengths, that is L goes to infinity, as you can see here. So your Q plus and Q minus are those inequalities which have to be greater than 0. So they take the minimal value when L is largest. So as you can see, that is sufficient to look at the semi-infinite interval. And these are again our analytic results that we have plotted. So for a special case, I can actually show you how this thing works. So if you look at Q plus Q minus, and you take mu plus and mu minus and initial mu's, and mu plus f and mu, and the final is mu plus f is equal to mu minus f is equal to mu. So it's a non-rotating final state. And we have taken a semi-infinite interval. So for that, Q plus and Q minus behaves like this. So one surprising aspect of this result is that if you start from the vacuum, mu plus I and mu minus I are 0, then you see that the whole thing vanishes for all time. It is surprising because the entanglement doesn't, if you go from vacuum to a finite temperature state, the entanglement doesn't thermalize instantaneously. It takes a lot of time. It takes time of order L/2 of the interval to thermalize. So exactly L/2, sorry. So now here, your T mu, of course, thermalizes instantaneously. It is surprising that S double prime plus this thing for a very larger length behaves like a 1-point function. It also gets saturated to the final value. So that, but of course, if it is not the initial state is not the vacuum, you get a non-trivial dependence, which is actually determined by the final mu. So this is one example. But anyway, so without going into many more such examples, let me just give you some allowed transitions. So suppose if you start from some mu plus and mu minus of this value, 1 and 0.8, you ask what are the other possible final states that do not violate the quantum null energy condition. And this is the answer that we get. So as you see that your mu plus, the final mu plus and final mu minus both have to be greater than the initial one, which essentially implies the temperature and entropy both should increase. However, it is not sufficient. So let us, for example, look into this graph. So we suppose we fix a final entropy density, which is simply mu plus plus mu minus is given by this straight orange line. It's a isentropic surface, isentropic line. Then you see there is this, these blue and orange lines are isothermal lines. So you see that they're bounded, the minimal and maximal values of T are bounded both from above and below, which is surprising because if you just use classical thermodynamics, everything here will be allowed, but quantum null energy condition is still violated. So, so this is the white region where it is not violated. I'll explain the gray region later. Similarly, you could see for this example, if you pick up a final temperature instead of final entropy density, there are bounds on the minimal and upper and lower bounds on the entropy density that is allowed in the final state. So this is a very, very surprising result. So for a given increase in entropy, there are both lower and upper bounds on increase in temperature and vice versa. So the black lines here are simply given by non-violation of QNEC at T is equal to 0. And these gray lines comes from later time evolution that you have to basically look at Q minus. Okay, I don't have much time to go into the details. So, but there are two crucial later results that I want to highlight. So whenever the transition is allowed, the Q plus always increases monotonically, and the Q minus always decreases monotonically with time. At an infinite time, we can exactly tell you what are the final Q minus and Q plus, and these are these values. So one interesting thing that you see that if the final state is non-rotating and you start with the vacuum, Q plus is equal to 0, which actually says that Q plus remains 0 for all time, recovering the result that we got earlier. And Q minus, so this is Q minus will always decrease and Q plus will always increase. So this is the result that we get. And actually we don't, so a more general result what we study is that if there is no energy momentum excitation that leaves the interval, then Q-neck inequality always behaves monotonically. And we do not really know why, because there's no good explanation for this behavior. So we would try to understand this better. Okay, so now let me come to another such example, which is Landauer erasure. So in Landauer erasure, what you do is that the basic Landauer principle tells you that if you want to delete information, it requires irreversible energy transfer for information carrying degrees of freedom to other degrees of freedom. So this is actually a statement that was made by Landauer in the context of classical statistical mechanics, but later Риeb and Wolf made a very concrete statement in the case of quantum statistical. The most important thing is there should be any irreversible logical operation must also involve irreversible thermodynamics, which is irreversible energy transfer or entropy increase. So one of the Landauer erasure protocol that we can study is that you basically start from a inhomogeneous Van-Adolph's geometry, and then you go to a homogeneous one. So you see in 3D CFTs, you cannot homogenize. It will not thermalize on its own because tidal excitations are live forever in pure gravity. So you need to do something. So you have to quench to do it. So this is a quench that you do. It's the same kind of geometries, of course, that we discussed earlier. It's simply that you are not taking a homogeneous state to begin with. And your L plus minus takes this form where Wx is roughly the deformation, is a diffeomorphism that allows you to do it. And this diffeomorphism, we take it to be Lorentzian, but L plus minus take this form. As you see that the classical null energy condition is violated here. But the state is allowed, no problem, because a quantum null energy condition is satisfied long before the quench. So there's nothing wrong with it. So yeah, so now you want to see how much of information that you are deleting here. So for that, you look at this class of excitations and you compute the entanglement for a large entangling length. And you see that the first answer comes out to be thermal, and the thermal has exactly this temperature d by pi. And then there's a finite piece, and then there is a terms that are suppressed by L inverse. So essentially, you can identify this as the amount of information that is there in the system that is non-thermal, that carries information. And B is the length scale that where information is localized. That you can see either from this Lorentzian form or from the form of L. You could say that you could easily see that B is the length scale where the information is localized. So now, okay, so now if you look into it, like what is the minimal energy that, so
I mean, maybe you can wrap up in 5 minutes, including questions.
5 minutes, certainly I can wrap up. Okay, so so what you do here is to look into the minimum amount of temperature increase that you need in order to not violate Q-neck and erase the information. So if you start with small localized, from large lengths where the information is localized, this final temperature increase actually grows monotonically with the amount of information. And actually you could show a very universal result that if the amount of information is large, or in general, if the minimum amount of delta T will be the maximum value of this Wx, if Wx is very large, where this Wx is this quantity generally. So basically it means that essentially minimum delta T would be essentially 6𝞹c of information at very large values of S info. That's what it means. But however, if you keep the localization, if you keep decreasing the localization length, you see that there is a funny behavior. There's a non-monotonic behavior of the amount of a minimum amount of temperature increase that you need in order to delete the information and not violate quantum null energy condition. And actually, this leads to a very surprising result. If you keep decreasing it further and study the thing, what you get is, I'll tell you how it later connects with that figure, is that there exists a minimal length, LC, for each S info such that if B is much, much later than LC, the information cannot be deleted suddenly without creating an infinite temperature state. So if you look into the, so basically, for this amount of S info, if you localize information beyond this length scale, you cannot delete it suddenly. Now, you see what will happen as SN4 becomes very, very large or very small, this localization length both go to 0. That's easy to see why it should happen in both ends. So when you have no information, basically, then basically you are going from one finite temperature to another finite temperature state. So delta T can go to 0 without violating anything. And similarly, you can argue for this large result, which is actually comes from this result, that there should not be any such minimum localization length. Okay, so but in
Sorry,
You got muted.
yeah, the speaker was muted. Yes.
You got muted.
yes, I cannot.
You're fine now. I don't know what happened. Sorry.
Yeah. Okay, I got muted. I don't know where I got muted. So I guess let me run through this again. So in this figure, if you have large amount of SN4, then the minimum delta T essentially scales with 6/c SN4. That's a result. That's a universal result. And here, what I want to say is that if you keep decreasing the localization length where the information is localized, you see the amount of delta T that you need in order to not violate the quantum null energy condition and to erase the information actually starts behaving in a non-monotonic way for smaller and smaller localization lengths. And then one thing that you see is that for any amount of SN4, there exists a certain localization length beyond which if you localize information in shorter length scales, you cannot delete it instantaneously without creating a final infinite temperature state. It's protected against very fast deletion. If you localize beyond this length, you cannot do it. And it's also easy to see when SN4 is less than is equal to 0, then you don't need any, there should not be localization length because you're basically a homogeneous state, finite temperature state, and you can simply go to the other, there's a minimum delta T is equal to 0 should be allowed. But however, if you keep increasing information, there exists this kind of a thing, kind of weird shape. And if you go for very large SN4, you can also say that your localization length, there should not be any minimal localization length, basically due to this formula. So you see this non-monotonic behavior. And so what will happen is as follows. Suppose I choose a localization length somewhere here, and I look into this curve. So initially, so this will actually go to infinity at some point, and again come back from infinity at this point. So there will be some particular value, some range of SN4 for which you cannot delete the information at all instantaneously. So that will happen. So that explains this non-monotonic behavior, which goes into two such weird things. It goes to infinity here, again it comes back from infinity somewhere here. So so this is how in middle there will be only complex solutions of your whatever analytic equations that we're using. So so this is how it behaves. And then you see the SN4 when it becomes C/6 roughly, when this SN4 becomes C/6, there is a maximal localization length. And this is sort of shape dependent. So this is a very new surprising result that I think you wouldn't have guessed just from the Landauer principle only. So I don't have time for bounding growth I simply go to the conclusions of my talk now because I don't have time for this. So for comments and outlooks is as follows. So we only talked about transition. We talked about transitions from between two homogeneous states and then from one inhomogeneous state to homogeneous state. But we can also ask, what about transitions between inhomogeneous states? So can we amplify an energy perturbation, or is there some kind of group operation that are allowed? So this is the questions that we are trying to look into. The other set of questions that are also equally important is to say now you can actually look into quantum matter in the bulk, and then you have to compute the entanglement entropy using the Engelhardt-Wald extremal surfaces, not the HRT extremal surfaces. And you can ask the same kind of questions like what QNEC allows, what QNEC not allows. But then you are basically asking some very important questions like, suppose you look into Hawking radiation and you are wanting to do some information task with it, how much resources you need for that, or how much of entanglement between the island and the radiation that is needed for that to happen. So these kind of questions are at the heart of resolving like the Hayden-Harlow kind of mechanism of resolving AMPS paradox. And also you could ask much deeper questions like, or the similar kind, what's the efficiency of quantum channels that you can create by using such quantum black holes? So these actually are goes very deep into the quantum information theory of gravity in general. Then you can also study other protocols like minimal entanglement require. So these are the set of questions that you can usually handle by this quantum. So we have set of collaborators whom we are exploring different aspects of this. And then you can also ask if QNEC is sufficient. You can also get why should QNEC itself work? You can probably get similar bounds from Rene entropies because QNEC uses entanglement entropy, but there could be some similar null. So there are some proposals that null derivatives of Rene entropies can give similar generalized bounds like QNEC. And similar, so we are also thinking along these directions. And also we don't have a real explanation why there's a monotonicity in QNEC that doesn't come directly from information theory. So we are exploring those aspects too yet. And the next question is that actually motivated by these set of questions is there really some good connection between resource theory and complexity? Because complexity is about building a gate and complexity literally takes you how you can prepare a state or something. And resource theory basically asks the same question in a very different angle. So is there some direct connection between them, which you can explore using holography? So hopefully I convinced you it's an interesting direction to pursue, and thanks for your attention.
Okay, thanks a lot, Ananda, for a very nice, Ananda, for a very nice talk. And so any quick questions? I think we are already a little over time, but because there's a break probably now, so we can have a few quick questions if there are, or any other comments anyone has. Okay. Okay, so maybe I can ask, one very, so at some point you were describing that, let's say if you go from the vacuum to the thermal state, there's some evolution of this entanglement structure, right? So, I mean, how much of this is in actual quantum field theoretic setup, or maybe in some lattice setup? Do you know if there is any understanding of that, when there is a thermalization process going on or settling down into equilibrium, is there any direct understanding of that from a, let's say, a lattice setup or something like that?
Yeah, very good question, actually. So yes, so of course, entanglement is something that you can manage to somehow compute in a lattice here. And I think there's there are DMRG protocols that study evolution of systems in real time, where they are able to compute how entanglement grows. I'm not sure it is very easy, whether it's very easy to compute something like the QNEC. So, or any analog of it. There are some proposals of analogs of QNEC in non-relativistic theories too. But I'm not sure if that is easily computable. So to do that, it's a good question to ask whether you can compute such things in this thing, in case of, say, a tensor network at least. So that's a good. In tensor network models, sometimes you can even compute analytically many of these things. And so I didn't get time to discuss, but we have really new analytic results for growth of entanglement, where like general cases for general transitions, which were not known before. It agrees with earlier results, and then there are bounds you could set based on QNEC. I didn't get time. It's on the slides. So like the diffusive growth from one initial state to final state, an exact analytic result in terms of the parameters, what is the diffusive constant and stuff like that. So these things are possible also to probably calculate to some extent in some tensor networks. So there could be comparisons that one can do based on it. But QNEC is a very hard thing to, and this is when we are thinking, we are actually trying to think about this question also, like how you compute it in a tensor network.
I see. Interesting. Any other quick question or comments? Okay. If not, thanks a lot, Ayanda, for a very nice talk. And I think we're going to close the session now. And so should we return at, I don't know, I mean, maybe I'll just give it over to Alok. And so at maybe 4:15, we can
Yes,
return?
you said, I mean, thank you. You spoke exactly what was on my mind. So I would request that we could reconvene 15 minutes from now at 4:15, 4:15, 𝗲𝗃 4:15. So Sudhakar, is it okay? Sudhakar, are you there?
It's fine with me.
Great. So we already have a first speaker. Tadashi is on board. So,
you can ask them in between to load their file.
Oh, yeah, I think that'll take about a few seconds. Arnab Rudra had a nice suggestion, which was very new to me. He suggested that we should explore Gather Town. Now, I'm hearing this for the first time. Please excuse my stupidity. So my team tells me it's an interesting option. They quickly Googled it and they already have a link set up for it. The only thing is that the free version can only take in 25 folks. So we'll probably tinker with it a little overnight. And I'll, they're going to teach me, and hopefully tomorrow onwards, the tea breaks will be more quote unquote interesting.
Good.
So, and additionally, so we are on the tea break formally now. Yeah. And in the meanwhile, I would also request the following. So all speakers have already been requested via email. I'm requesting again to kindly share your presentation files. As I was intruding in a couple of talks post-lunch, I apologize, but it was just to convey that all those who have shared their presentations, their files are already uploaded. Both and the videos of all the pre-lunch session speakers are already uploaded. And if you recall, this is a remark I made at the beginning today morning, that our tech support team literally works in real time. And this is, I think, a very good supporting case for that. So please do share your profiles. We really appreciate that. And I would shut up now. And I guess in 30 minutes from now, Sudhakar is going to take over. So see you then. You're welcome to hang around. We're using the same link. It is one link for the entire post-lunch session, as well as the discussion session.
Good.
Thank you.
Hi, Sadaka.
Hi.
Hello.
Yeah.
Good to see you.
Yeah, good to see you. Nice to see you. Yeah. So we are waiting for a couple of more minutes. And so people have gone for a tea break, so they will come back and we'll start.
Maybe 5 minutes or so?
Maybe less than that, 3 minutes.
3 minutes?
3 minutes.
Okay. Can I test my slide?
Yeah, you can check in between. Yeah, it will be better for me. So
yeah,
you can share yours.
Yeah, I'm doing this. So can you see?
Yeah, I can see it. Go to the title page.
Okay, title page.
Yes.
Okay.
Yeah.
Thank you very much.
Okay.
Thank you.
Hello, can we start?
Yeah, by all means, you're the boss.
Okay, so we
And
start.
maybe just a little reminder, I mean, in case it is necessary, it's half hour is essentially 25 plus 5, the talk and QA.
That's right.
Yeah, thank you. Thank you so much.
Okay. Good afternoon to you all. Welcome to the post-tea session of this meeting. In this session, we have 3 talks, each of them half an hour each. And I request all the speakers to have the talk for 25 minutes. 5 minutes we'll have question and answer, and basically for short questions. Since our session will be followed by the discussion chair, other long questions can wait for the discussions. If it is okay, then I will first invite Professor Tadashi Takayanagi to give his talk. He will be talking on holography in de Sitter space via Chern-Simons gauge theory. Tadashi, over to you.
Thank you very much for. I'd like to thank organizers for inviting me to this really wonderful Indian Strings meeting. So here I'd like to talk about our recent work about related to DS-CFT, holographic dual of de Sitter space. And especially we focus on 3 dimensions by using the Chern-Simons gauge theory. And this work is based on this preprint and some work in progress. And with 𝗤𝘃𝗀𝗃 𝗃𝗃 and 𝗪𝘃𝗀 𝗃𝗃, they are both faculty member in our institute. And 𝗰𝗵𝗶𝗿 is our graduate student. Okay, so let me start with the introduction. So the basic question, what do we expect for DS-CFT, de Sitter CFT correspondence? As we all know, so ADS-CFT provides a non-perturbative formulation of quantum gravity. So of course, this is for negative cosmological constant case, and it's quite well understood. So quantum gravity or string theory on D+1 dimensional anti-de Sitter space is equivalent to conformal field theory on D-dimensional space. This D-dimensional space is typically lives on the boundary of anti-de Sitter space. And especially very interesting limit is a classical gravity limit, where quantum gravity just reduced to general relativity with negative cosmological constant. And in the conformal field theory side, this corresponds to large n strongly coupled limit. And so we end up with strongly interacting CFT. So we can analyze strongly interacting CFT using more classical gravity, and which is quite useful, and a lot of application of ADS-CFT. And on the other hand, our understandings of quantum gravity for space-time with positive cosmological constant, namely de Sitter space, have been highly limited. And one interesting possibility to understand such a quantum gravity on Dojita space is to explore some holographic duality, especially which is called ds-CFT correspondence. So first pioneered by Strominger and also Witten and Maldacena. There are lots of interesting works. And this is one sketch of this ds-CFT correspondence. So here we have in mind some Hartle-Hawking description of a Dojita space. So we have a Euclidean path integral, which gives some kind of tunneling from vacuum. And we continue to Lorentzian time evolution. So this is quite usual. So we start with sphere, semi-sphere, and goes to Dojita space. And then at time goes to infinity, we end up with space-like boundary. And usually holography relates bulk to boundary. So this is a boundary. So Dojita space, there are no time-like boundary, but we have a space-like boundary. So this is space-like boundary that means maybe, and also because of the symmetry of Dojita space, we expect some Euclidean CFT, some Euclidean conformal-Fuseli symmetry. So maybe we can think this is there are some Euclidean conformal-Fuseli on this space-like boundary, namely d-dimensional sphere. And if holography is true, even for this case, should be dual to some gravity on Lorentzian Dojita space with some Euclidean nucleation of the space-time, but it's Dojita space, d plus one dimension Dojita space. This is a basic idea of ds-CFT correspondence. And in other words, this Dojita space, if we think Dojita space, it's a Hartle-Hawking wave function, which is basically a partition function with some fixed metric at the boundary. It's equal to CFT partition function on this Euclidean CFT on sphere. But however, we should note the following fact that, so we know regular Euclidean holographic CFT should be dual to Euclidean areas, not the ds, because this was just some part of areas CFT. So here, but anyway, we also encounter some Euclidean CFT. So if this CFT is dual to Dojita space, that should be sort of some exotic conformal Fuseli. It's unusual CFT. For example, there are some nice example worked out by Ninos, Hartmann, Strominger, that so for this four-dimensional case, four-dimensional and also higher spin Dojita gravity, which is not just a standard Einstein gravity, but with many more higher spins, but it's a kind of classical gravity. And four-dimensional higher spin gravity is proposed to be dual to three-dimensional SPN vector model. But it's not ON, but SPN means it's kind of, it consists of n anti-commuting scalar fields. That means basically ghosts. It's a series, it's like a theory of ghosts. So it's in that sense, it's a bit like exotic. And another evidence that such a dual Dojita space is exotic is maybe looking at the holographic entanglement entropy. This is basically, so these are based on the work in the next speaker, Narayan. And if we calculate, just try to calculate holographic entanglement entropy, assuming Einstein gravity in Dojita space, we encounter some very complex valued entanglement entropy. And as we also mentioned, the central charge also becomes complex value depending on the dimension. But anyway, because of that, so example of CFT dual to Einstein gravity. Here it's for example higher spin case, but if we talk about Einstein gravity, I don't think any definite example has been known so far. So anyway, we want to construct some gravity dual of Einstein Dojita space, and that is still missing. And then to give one possible answer is the main part of this talk. But I should mention that there are other ideas of the ds-CFT. It's a little bit different from this kind of picture. They're using different patch. And so idea is ds-ds duality and using TT bar and static patch holography and the surface state duality. There are also other approach which involves less the exotic CFT, more exotic, more standard CFT is involved here. But I'm not going to talk about this. I'm more focused on more kind of old-fashioned or more traditional ds-CFT correspondence here. And so then I'd like to discuss what do we expect for ds-CFT. Let's assume just general framework of ds-CFT and what we can at least say about the dual CFT. So let's assume Dojita Einstein gravity, which is the simplest. We are interested in classical Einstein gravity and extract general expectations. And so we start with d plus one dimensional Lorentzian Dojita space. This is a global patch of Dojita space, and we can go to easy. It is well known that we can just analytically continue or go to Euclidean space. Euclidean version of Dojita space is just sphere, right? So we can just t goes to I theta plus something pi over 2. then we get this metric, just sphere. And if we want to go to anti-Dojita space, so we need something more that we should take an imaginary radius. So imaginary value of imaginary radius of ADS correspond to real valued radius of Dojita space. For example, this is Maeda Senat's old paper discusses this in very clear way. And so we can also theta coordinate angular should be continued to imaginary value so that we get a radial coordinate low. Then we get Euclidean ADS, right? This is just very simple mathematics. And then, but this already shows that something exotic happens here. So if we consider central charge, and we can define central charge by ratio of ADS radius divided by Newton constant, ADS radius to this d minus 1, d is dimension, d plus 1 is dimension of gravitational spacetime. And this ratio is typically we call central charge. And in terms of Dojita radius, let's assume Dojita CFT, that means Dojita radius is real value. Then actually this is real value, so we have to put I here. So I d minus 1, and then depending on d, so especially even dimensional case, d is even, then we encounter imaginary value. This part is become imaginary. So even means total dimensions, total space-time dimensions, or odd dimension, like ADS3, ADS5, then we have imaginary central charge. So what we at least learn here is that central charge becomes imaginary if d is even. This is the case we are interested in. But one more important thing is that this ratio definitely should be very large if we talk about classical gravity. ds radius should be much larger than Planck scale. So central charge should get very large. Absolute value of central charge should be very large in classical gravity. This is something we know very much in ADS-CFT case. Okay, so these are two inputs. So I just finished the introduction, and basically I explained what do we expect for the SFT and give some explicit construction of two-dimensional conformal field theory expected to be dual to DS3. And we discussed this correspondence by looking at partition functions and discuss some higher speed holography and some correlation functions and finish this talk. Okay, so let me give some our construction. But before that, I explain something well-known fact. I'd like to explain something we know very much. So first fact we know very much, and also this is a motivation why we consider three-dimensional Dojita space rather than higher dimension. 3D is something good, right? Always some interesting solvability appears. And we know very much that Einstein gravity on 3D Dojita space can be written equivalently written in terms of 3D Chern-Simons gauge theory with gauge group double copy of SU2. SU2 cross SU2 we call Ayan. This is a well-known fact explained by Witten. And so here we just follow standard notation of Chern-Simons gauge theory. So we have this Chern-Simons action with I here. And we pass integral with IK and this Chern-Simons integral. This is just a standard definition partition function in of so standard partition function of Chern-Simons gauge theory. But actually, so to relate this to Einstein gravity, we have to take this K, this level, right? This level should be imaginary variable. And once we plug this everything, this I is cancelled, so we just get a standard Euclidean action, which is real variable. So this is something very much well known. So we have so in other words, it's a radius of Dojita space corresponds to large level limit of Chern-Simons theory. Okay. And then I would like to also mention another well-known fact. There are also two works by Witten. So this is a relation between 3D gravity and Chern-Simons theory. And this is a famous John polynomial paper that is related to this relation between Chern-Simons gauge theory and the Wess-Zumino-Witten model, conformal field theory. So this is called also kind of toy model of holography, or this may be first example of holography, Chern-Simons holography. So because the CFT, 2D CFT is dual to somehow this three-dimensional theory. And if we focus on SU2, so SU2, Chern-Simons gauge theory at level K is equivalent to conformal blocks of SU2 Wess-Zumino-Witten model at level K. And here are some sketch, which is also very useful in my talk. So we define partition function of Chern-Simons gauge theory is just dA. So here we assume, so sorry, this is a double copy of SU2, but you can just cut it. You can just cut it one of them. For gravity, we need two of this. And we have some Chern-Simons action and the Wilson roots. And so basic idea is kind of a topology argument based on the surgery. So we can paste two manifolds together. Then we get the partition function also factorized, and we can just get the result by just multiplicating partition function, each partition functions. So also we have a modular transformation. This is a kind of solid torus, and with one Wilson line, and we can do some S transformation. Then we get this kind of rotated solid torus, and then coefficient is given by S matrix. S matrix here. This S matrix is in SU2 is well known, right? This is text used in any textbook, like the sign and the K+2, and this formula is very important role in this talk. And also, if we wanted to calculate partition function on sphere S3, then we can just attach. Here we didn't write, but maybe we can put S3 with some Wilson line like this. So with one Wilson line, then we start with some solid torus with one Wilson line, Wilson loop, and also just vacuum solid torus and paste with each other. But this guy is related by S transformation. So we have to multiply S here. We just get S here, and that is we get S matrix here. And if we are interested in this linked loop, then we can separate this into two parts, like this one solid torus is one Wilson line, and another flat torus, but it's rotated maybe 90 degree rotated, or a modular transform solid torus with one Wilson line and paste with each other. Then we get this linked Wilson loop, and because of that we get this because this guy is rotated by this S matrix, so it's just we get this single S matrix gives partition function. And finally, if we talk about two unlinked Wilson loop, it's just like we can decompose this way, and then these two guys are each S matrix, so we get this relation. Okay, so this guy and this guy is something we know very much, but because this is already it is very suggestive that maybe 3D Dojita space might have some CFT dual. But I want to make this more precise. But for this, we have to first note one basic puzzle for this. So by employing the fact, we explain two facts, and based on the old Wittgen's paper. And one may suspect 3D gravity might be related to SU2 S-Lumino model, and through this SU2 cross SU2 Chern-Simons gauge theory. However, this does not seem to work as it is, because the Einstein gravity limit is we have to take K goes to very large, right? As already explained. K goes to large. But if we talk about the SU2 Wess-Lumino model and calculate the central charge is well known. This is quite well-known formula in textbook. And if we take K goes to infinity, so this goes to 3, right? On the other hand, the standard result for the DSCFT for Einstein gravity predicts that central charge should be very, very large. So how it's going? And we'd like to claim, actually, we should take other limit. So K goes to -2 limit to realize DSCFT duality in a clear way. But actually, this is related to this one in the end, as we will explain in the end. But apparently, we can take this limit. So K goes to -2, but a slight small deviation given by I times something. And this is just very small if Dojita radius is very, very large. LDS is Dojita radius. And if we plug this in a formula, famous formula of central charge, we just get large value because this, right, denominator becomes very, very small. And so it gets very large. And plus also becomes imaginary value because we put I. So this is, and this is exactly the central charge, what we expect for Dojita central charge. And yeah, and if we talk about, this is just vacuum set, but if we want to excite, right? Think about the excitation, then we can, relate this conformal dimension of S-Lumino model. This is a primary conformal dimension primary field with spin J. This is well-known formula, and this is also equal to imaginary I times energy of Dojita space. This is also very usual in DSCFT formulation. Okay, so, but of course, I just said this, and this is our claim is just this one. So K -2 limit SU2 with S-Lumino model, where energy central charge goes to very large, but imaginary value, and it's dual to 3D Einstein gravity on Dojita space with very large radius limit of Dojita radius. But of course, we have to check, right? So, and one may wonder if our limit can really correctly produce Einstein gravity, right? This is given by this action. So below, we'd like to compare the partition functions. So here, partition function is the partition function with Wilson loop in that. So to make everything more interesting, so we put some also Wilson loop. And just to come from this relation, just using this relation, we can rewrite this way. So 1 minus 8 GEJ, this is quite the interesting combination which appears everywhere. This is written in terms of conformal dimension. And it's like related to the spin of this primary, so J plus 1 square. And the important here is the actually most important part. So this is a well-known formula of S matrix, but we have a denominator as a K plus 2, right? If we take K minus 2 limit, then this gets very large. And if we take imaginary value, it's like becomes sinh, right? And that is means exponentially large. This is the I is cancelled with this I here. So it's basically exponentially large. S matrix becomes large. We analytically continue level to this complex value. And then, so we can also compare this, so we can evaluate this partition function with a single Wilson loop, right? This is just RJ is a representation of this Wilson loop. And we can evaluate this S matrix. And this is now square because we have SU2 cross SU2 because this is a gravity. Chern-Simons gravity has two different gauge groups at two different connections. And this is exactly because of we can just use this evaluate here and using this formula is just given by square root minus hg Newton constant in J. And already here, if we set the E equals 0, right? Energy 0, this is just we get this one. This is precisely Dojita space entropy, 3D Dojita entropy. And the gravity dual, and then we can talk about the expression. Here it's just Chern-Simons calculation. This is a kind of CFT calculation because using SU2 based model. So here we are talking about 3D Dojita space. Just to now go to gravity side, just Einstein gravity. And here is tau is periodically identified like this way. And so the on-shell action, so we can evaluate this. This is just a Dojita black hole solution, right? If E is 0, this is just a regular static patch of Dojita space, but otherwise just Dojita black hole. And tau is periodically identified because there are no singularity at the horizon. And then we just plug this in on-shell action, we get correct, we get this result, and this is precisely agree with this result. Right? So is the CFT correct computed CFT SU2 based on the model, it precisely agree with this gravity action. And we can, so here we can a little bit remind what we are doing here. So this is very parallel with what people do to calculate topological theory, like Chern-Simons theory by the surgery. So here, this is a metric. We can but introduce theta by this way. Then it's actually what we are doing here is just to theta. Let's separate theta 0 to 4pi/4. This is the solid torus, and theta 4/pi to pi/2. So pi/4 to 4. This is another solid torus, and we just paste to each other at theta equal 4pi. And here we have some actually deficit angle. This tau theta equals 0. At the origin, actually, there are deficit angle, singularity in this geometry. But at the horizon, black hole horizon is here, there are no singularity. So then they paste to each other. And this is precisely looks like this Wilson loop, one Wilson loop in that, and it's quite natural. These two guys agree with each other. And we can go further, and we can talk about double Wilson loop. And this one example is a linked case, we get this result. And this separated case, this unlinked case, we get this result. It looks like this is multiplication, this is sum. It looks so different. But nevertheless, we can precisely reproduce from gravity side. And in this first case, the other cases are coming later. But first one is just, we just very similar to previous one. We introduced two deficit angle. This is already here, but also we introduced one more deficit angle so that the horizon, on the horizon, it's a bit singular. So then, these are details, and we both have a deficit angle and just calculate, partition function of gravity is precisely agree with this action. This result. So can I post one question at the end of this talk? Or
yeah.
Okay, so it seems maybe
small question, or we can keep it towards the end.
Okay.
I think as you go ahead, we'll keep the questions to the end.
Okay, let me wrap up soon. So here, anyway, so we talked about Einstein gravity and some nice matching of partition function, but we can also talk about the higher spin holography. And so here we can just generalize the SUN, right? But for this case, the level K should be take to minus n instead of minus 2. But the other things are basically the same. And the only non-trivial, just more sophisticated Lie group of structure here. This is inner product. The lambda is a weight vector of representation of primary, and this inner product is just standard Lie algebra. And so here we can talk about Chern-Simons. This is two-dimensional model S matrix, and it's for this limit. In this limit, K goes to minus n. It looks like exponentially large, like this way. And this we can also from sophisticated some a little bit after some work, so we can reproduce same result by looking at the higher speed gauge cell. So just we can find a nice solution which precisely gives this value. And then anyway, so that way, and we can also explain this analysis by decomposing this way. So we can explain this, unlinked result, and which is just sum, right? Not multiplication by this way. This formula also explains that. And and one more important point is that actually it is good to useful. It is very useful to remind higher spin holography worked out by 𝗲𝗃𝗿 and 𝗏𝗂𝗏 that this is in this case this W minimal model like this coset is equivalent to 3D higher spin gravity with some lambda. The lambda basically variable spin. And so here we take this limit to Hooft limit, but in our limit anyway, K goes to minus n. This has only this part gets a infinitely large central charge. It's natural that this part dominates everything. So not so different because there are other factors, but it's kind of subdominant in this calculation. But moreover, this 𝗲𝗃𝗿 find very surprising symmetry called triarity. And that triarity replaced, so n is the rank of this, so SUN is n, and lambda is this Hooft coupling. It's a kind of like ratio. And we can flip this.
5 more minutes.
Yeah, just finished. So there we can flip this, and then still get the theory is the same. So if we do this in our limit, K goes to minus n limit, actually lambda prime now goes to n. And this means that n is a spin, so we get some classical n spin, n gravity, and we assume everything just analytical continue to those space. This also suggests that we get some n equal to gets Einstein gravity on Dojita space. And we have nice matching of this partition function. Okay, and 2-point function. I'm not enough time, but for this case, we only talk about Euclidean, so we can explain this part of 2-point function, but we can naturally continue to Lorentzian evolution and to get some 2-point function of dual, maybe two-dimensional conformability with �𝗏𝗏. Okay, so basically they're all of my talk, and just finished my talk with conclusion. So in this talk, we propose a CFT dual of 3D Dojita space in the Einstein gravity and its higher spin generalization. And our claim is K goes to n minus n limit with SUN with �𝗏𝗏 model is actually dual to classical spin and gravity on 3D Dojita space and the radius. And so we confirmed the agreement of partition function, and we studied so future problem. So we studied this and partition function, but the future problems are Lorentzian dynamics and details of basic model because it's an unusual limit, negative level limit, and it's quite interesting to work out quantum corrections, and finally it's interesting to think about holographic entanglement. I think I will stop here.
Thank you, Tadashi, for a nice talk, and
thank you very much.
Almost keeping the time. I can see already lots of hands up. We can start one by one. Spenta, you can go ahead with your question.
Okay, hi Tadashi.
Hi.
Very, very interesting talk, very provocative. So, I mean, my question is an obvious one, that K going to minus n limit will lead to non-unitary representations, right?
Yes. I think so. Yeah.
So that doesn't bother you?
I think, yeah, in that sense, anyway, we expect some gravity dual of Dojita space can be non-unitary. Because if it's unitary, it's usually dual to Euclidean anti-Dojita space. So anyway, I mentioned, but it seems to be very exotic gravity. As long as we see this, if we talk about gravity dual at future infinity.
Yes, but my worry is that an observer sitting there in that space-like slice will be dealing with a non-unitary field theory to work out his correlation functions, etc. I would be a bit worried, but I just don't know enough to say anything.
Okay, but I agree. But also recently there are some actually mathematicians working on this kind of unusual limit, at least representation theory. And there are, for symmetry-wise, there are many new results is known, and to study also this kind of duality relation, and where we have to continue to level K to be a non-integer value. And so I hope that that's really helpful to understand also.
We can keep this for the discussion session, which is going longer. Okay, Sunil, you had also put up your hand. Please go ahead with the question.
I think Souvik put up his hand before me.
It's all right. I mean,
it's a different color. Okay, Souvik, please go ahead.
Okay, so I had a question about this this CFT which you're working with. So this, you're taking a limit of a rational theory, which means that your light spectrum is not sparse. I mean, usually in ADS CFT, we want, like, if we are looking for a theory with Einstein gravity dual, our light spectrum should be sparse so that, you know, we have a Hawking-Page transition in the bulk. But I don't know what the analog of that is for DS-CFT, but since you're working with a rational model, my worry is that, like, I mean, since there are a lot of number of light states, shouldn't you expect more fields in the bulk instead of just having Einstein gravity?
Okay. So, but yeah, that's good, very good question. And so far we don't know full spectrum, to be honest, because we didn't construct full modular invariant partition function, for example. We are only working at the level of representation, such as symmetry. And also we worked only for this vacuum partition function. And that is we can determine this vacuum partition function only by looking at this S matrix. And so we are not talking about this, what kind of spectrum are there. So that is actually next order question. And this also involves quantum correction. How this, so multiplet, what kind of multiplet in this gravity improves?
You expect that the full agreement of the spectrum might lead to a different theory, right? I mean, it may not be this. I mean, this might capture some part of some sector of it, but it may not be the full.
So we don't know what kind of matter exists in dual gravity. So we're not saying this is just dual to pure gravity.
Okay. And just a related thing is that, I mean, since you said matter, I mean, one of the things about the Gabriel-Gopakumar duality is that they had a scalar which was had a very precise dependence on lambda for an agreement of partition functions. So yes.
I think that's the next order question actually. So what we talked about is only this piece of this SUN, basically. And there are other ingredients if we talk about this Gabriel-Gopakumar duality, and that gives, as I said, as a scalar field. But here we only talk about this main part, and just as correspond to large, classical gravity limit. And so maybe we can even modify, we can add even other sector of CFT other than this one, and to change the Dojita gravity. So the gravity part is same, but we can add many different kind of matters, and that part is there kind of redundancy, I think. That is a very interesting question, but this, for us it's kind of next question.
Thank you.
To be asked.
Sunil, go ahead.
Tadashi, I had this puzzle, and if we look at ADS gravity and write it as Chern-Simons theory, then the dual is supposed to be some pure CFT with only Virasoro symmetry at large central charge and so on. That is the Brown-Hainaut construction. And somehow that dual theory, it doesn't have any spin one currents, right? It's really a pure Virasoro CFT. At least that's what I think is believed. But somehow here in a very similar context, but instead of SL2R, you're using SU2. Now the boundary theory is supposed to have, I suppose, should have spin one currents corresponding to your spin one gauge fields in the bulk, right? So do you have any comment on that? Why the ADS and DS cases behave so different with respect to the matching of fields on boundary and bulk?
Okay, but So you mean current is just SU2 current? You said it's because spin 1 because we have current.
Yes. But in pure in ADS gravity, there's not supposed to be any current in the bound. No spin 1 current in the boundary.
Yeah. Okay. Yeah, but to be honest, that part I'm not sure because actually the thing which really dual to pure gravity part is sort of dual, like CFT, which is included in SUN. And there are other pieces. It is true, but that part actually somehow don't contribute to the S matrix in this limit. And it's not so easy to distinguish the presence of this other sector than a pure gravity limit. So maybe we can construct some gravity with also current algebra, but also we can remove it by also in this case we can remove by taking coset.
So you think the boundary theory might be actually a coset rather than SU2?
Yeah, that's one. If this is true, I think so. Yeah. Yeah, but I think maybe, but our analysis so far it's very still primitive, and that we can allow many different possibilities. We can add maybe other also sectors. Still, this pure gravity part doesn't change actually.
I see.
As long as S matrix is same, almost same, then other part is not affected. Yeah.
Thank you.
Navamita, please go ahead with your question. Navamita, can you hear me? Please unmute yourself.
Yeah, she's muted. Maybe if she's not there, you can go on to Sandeep.
Can't you hear me?
Yes.
Yeah. So what I'm saying is this Tadashi, this construction also almost similar for flat space case as well, right? For Einstein gravity in flat space. So in that case, does this partition function equality works?
Sorry. Flat space case, you're asking? Yeah, sorry, we haven't tried this flat space dual, but it is true. So flat space holography also we can describe it to Chern-Simons gravity.
Yes.
So that's that sounds interesting. But we didn't confirm that. So we didn't compute for that case. I think it's quite an interesting question.
Thank you.
Okay, Sandeep, please go ahead with your question.
Okay, thanks, Sudhakar. Thanks, Tadashi, for a very nice talk. I've got one quick clarification, and then I come to my question very quickly. The clarification is, are you working with SU2 or SL2 or Chern-Simons theory?
SU2, yeah.
I see, but ultimately, isn't your formula for central charge more like 3K over K minus 2? And then
I think, you can continue that way. SU2 and SL2 are also, they analytical continue to each other, in my understanding.
But partly the reason I'm asking, and then I'll come to my other question is, we've tried to quantize BF theory in one law, which is a compactification of Chern-Simons theory on a circle, if you like, and which is related to JT gravity then in one lower dimension. And you can quantize JT gravity in de Sitter space. And the quantization is very closely related to JT gravity in ADS space. But there are important differences in the DS case having to do with how you analytically continue the ADS2 theory to DS theory. And one example of that is, and now let me just ask the question to you, do you have an amplitude not only to produce one universe, but also two universes out of nothing?
I see. But here, actually, we are really doing some very rigid calculations that we are looking at the Euclidean partition function, namely S3.
Yeah.
And it seems just it create one universe because just it's S3. Even if we think just semi-sphere, it's creating from nothing to just one Todita space. But you can some of different topologies, then I think that's possible.
Yeah.
But here we didn't do that. So but it's quite interesting that we can think that version we also sum over.
Wouldn't the Chern-Simons theory allow for a path integral with two boundaries?
Path integral with two boundaries. In this case, I see. So we have to create two universes in this analysis. I see.
Okay, just.
Yeah, sorry, I don't have a quick answer to that question, but it's, yeah, interesting.
No, just to say, because in the BF version, which is, I think, just a dimensional reduction, at least if you work with the ADS2 version or the analytic continued DS, then you can get also two boundaries and many boundaries. And the two boundary can be interpreted either as producing two universes out of nothing, or if you analytically continue as a transition amplitude from an initial universe to the final. And all of this happens because of the subtlety between ADS and DS, you know. So that's why I was wondering if there's a parallel here. But okay, anyway.
Yeah, sorry, it's also this reverse three-dimensional manifolds rather than 2D. So maybe some difference can be, but as far as, because we know it's also 3D can be reduced to 2D, some compactification. I think we are probably what you are, I think, also parallel with here. But yeah, I should think more carefully to understand, to creation.
Are there any more questions from 𝗦𝗂𝗀𝗶𝗿 seminar room? I can see the hands up. Are there any questions from there?
No, sir.
Okay, thank you. In that case, Arindam, please go ahead with your question.
Yeah, so I had two questions. So if you naively try to reduce the 3D, gravity starting in Chern-Simons formulation and write it as a Wiedź-Newton model in de-Sitter, what you get is a constrained Wiedź-Newton model, right? So you get a Wiedź-Newton model, like you said, but the phase space is constrained through some extra conditions. So are these constraints affecting the calculation of partition function that you're doing here?
So what do you mean precisely?
Sorry. So in order to actually reduce from Chern-Simons to these Wiedź-Newton type models, you need to analyze some asymptotically de-Sitter, the phase space of an asymptotically de-Sitter space times in 3D. Okay, and that imposes some conditions on the Chern-Simons action, which you can show that reduces to Wiedź-Newton, but it still leaves some constraints behind. So there are some extra constraints that needs to be imposed on that Wiedź-Newton theory, which, for instance, can be used to reduce this Wiedź-Newton theory to further to a Liouville type theory.
Okay, yeah. I see.
Right. So while calculating these partition functions, for instance, are those constraints, important, or where are they used?
Yeah, that's a good question. Yeah. So there is also possibility that there are some extra constraint, as you say, but that constraint actually does not affect this partition function analysis, because S matrix also, actually I didn't mention, but this same S matrix we can get from Liouville theory. And that case, it's like a Hamiltonian reduction, like constraint appears. Right?
Oh, okay.
But it's not so easy to distinguish these two, to be honest, in our analysis. But to understand that, I think we need a quantum correction. We should talk about 1/c corrections and so on.
Right. And another question that I had is that these works of Maloney and other people on this 3D de-Sitter calculations, in Euclidean de-Sitter partition function calculations, they have these length spaces as the class.
Yeah, I know that. Yeah.
Yeah. So what would that correspond to in these Wiedź-Newton picture, for instance?
Length space. Okay. Yeah. Okay. That. Yeah, so that case is, manifold itself is changed, right? And so this is not S3, so so not so simple, right? Because SU2 is really related to this S3 geometry, right? It's come from symmetry of S3.
Right.
So it's not so obvious to me. But it's probably kind of related. We can still describe everything in terms of this S matrix of SU2 SV model, in my understanding. Right. So it's maybe some kind of overfold or some such as some kind of non-trivial quotient correspond to that length space, I think. But sorry, I don't have a definite answer to that.
Okay. Thank you. Thanks.
Siraz, please go ahead with your question.
Hi, Tadashi. Hi. Sorry, I missed the first few minutes of your talk, so you may have said some of this then, but I wanted to ask, suppose you took just the usual k goes to infinity limit, then the SU2 Chern-Simons theory would be sort of guaranteed to reproduce gravity.
Yeah,
right?
yeah, exactly.
So if you did the same calculations in the SU2 Chern-Simons theory at k goes to infinity, you will also get the results of de Sitter gravity, but with a different constant, with a different identification.
Yeah, yeah. So I think that is really this triarity here. Sorry, I mentioned it here. So yeah, if we take, so we know the k goes to infinity is just gives classical gravity limit of digital space, and that corresponds to this this limit. So this is a higher spin gravity, but if lambda equal 2, then this is just Einstein gravity and digital space, and n goes to infinity. And on the other hand, our limit corresponds to k goes to -n. And this limit is precisely your limit, what you are saying.
I see. So both things are true, and it's explained by some sort of triality. You're saying. Okay, thank you.
I think so. I think so. But it's, of course, we extend that to digital regime, so it's highly non-trivial.
Sorry, I didn't hear what did you say? You
so we just analytical continue what we know for triality for ADS to digital.
Yes.
Then
Okay.
that is yeah.
Okay, thank you.
Thank you very much, sir.
I have one question, please. In this question model case, both k and as well as capital N are positive numbers. How do we take actually one positive number, a limit one positive number going to negative of another positive number?
Okay. Yeah, k we take k can be negative. So k originally positive, like integer value in standard erasure model, but we analytically continue k to any complex value. But n is here. N is real positive value here.
N is positive, of course, right?
Yeah.
So first after the analytic continuation, you take the limit.
Yeah.
Okay. If there are no more questions, if there are any more questions, please we'll keep it to the discussion session. So let's thank again Tadashi for this nice talk, and we invite the next speaker.
Thank you very much.
Krishnan, are you there?
Yeah. Hi, Sudhakar.
Yeah, please try to share your screen.
Yes. Can you see this?
Yeah.
Okay, so shall I begin?
So the next talk is by Narayan from CMI, and he will be talking about cosmologies, singularities, and quantum extremal surfaces. It's almost 5 o'clock. So 5:20 up to 5:25, you can go ahead. Around 5:20, I will give you a signal.
Sure, thanks. So it's a pleasure to be here, and I'd like to thank Alok and the organizers for this this nice conference and the invitation to speak. It would be great to be in Roorkee, but this is pretty good also. Am I audible, by the way, just to check?
Yeah. Sorry.
Okay. So I'm going to talk about aspects of cosmology, singularities, and quantum extremal surfaces. This is based on these two papers and a collection of people. 𝗲𝗏𝗏 and Partha are postdocs at CMI. Manu was a student at CMI. Hitesh and Kaveri are currently beginning students at CMI. So I'll talk about certain aspects of ADS cosmologies and classical RT-HRT surfaces to begin with, and then I'll talk about quantum extremal surfaces, towards which I'll talk about two-dimensional formulations of these theories. And in the last part, I'll talk about null Cosmos singularities and quantum extremal surfaces. And if time permits, towards the end, I'll talk about certain aspects of de Sitter. So it's nearly 25 years since ADS-CFT began, and it's still quite interesting and important to understand time-dependent phenomena in string theory and holography. There have, of course, been various studies over the last many years. So I'm going to focus on trying to ask questions about Big Bang or Big Crunch singularities, where curvatures and tidal forces diverge, and so you would expect that GR and general relativity and notions of space-time geometry break down. The hope might be that holographic or some stringy description provides a UV completion and marches on. Okay, so in the last several years, we've seen entanglement as a very insightful holographic probe. specifically in terms of classical RT-HRT surfaces and quantum extremal surface probes in more recent times. Okay, so so this is going to be the theme of this talk on studying aspects of these sorts of extremal surfaces and these kinds of cosmologies with singularities. But before going there, maybe it's useful to have a prelude for singularities and string theory at a very broad brush level. So of course, we know that there's a long history of studying singularities and their resolution in string theory. So for orbifolds, for example, just conical singularities, spatial conical singularities, we know that these are singular for point particles, but strings have extra light winding modes. Okay, and these provide resolution modes of the singularity. This is well known. Null singularities are essentially singularities in time, but in light cone time. We have examples like singular plane waves or null Carstens singularities, which are equivalent. And it's again known that strings can be quantized explicitly in these kinds of backgrounds. And what's been known is that strings become highly excited in the vicinity of the singularity. Space-like Big Bang or Big Crunch singularities are somewhat unclear, it's fair to say. So there are again several toy models, well, not too many, but several toy models of holographic cosmologies with Big Bang or Big Crunch singularities, and some of them I'll talk about. So the bulk gravitational description breaks down, and you might ask questions about whether the dual field theory provides the right variables to go past and to march on. I won't have much to say concretely on this question, but it's probably a good idea to keep this broad question in mind about what are resolvable singularities in string theory and holography. Okay. So with this prelude, let me just go on to talk about old work actually on ADS cosmologies and duals, and then more recent work where we studied classical extremal surfaces. So here is a prototypical example. So this is the isotropic ADS5 Kastner space. It's basically a space where this Kastner space-time has been embedded in a particular way. And you can see that at t equal to 0, there's a space-like Big Crunch singularity. If you look in terms of the dual theory, you can see that the gauge coupling goes like e to the psi, which actually goes to 0 as t goes to 0. So you might ask whether this is actually given an example, suggesting a weakly coupled CFT at the location of the singularity. And if that were true, then that would provide a way to continue past. Okay. In detail, it turns out in a series of in a body of work with Sumit Das and Sandeep Trivedi and Adilawad and Jeremy Michelson, Suresh Nampuri long back, what we ended up finding was that a weak coupling analysis, if this were true, you could ask questions about a weak coupling analysis of the dual field theory, and this suggests that this actually shows that interactions are in fact important, and the gauge theory response ends up appearing singular. Null singularities appear better. Null singularities, by null singularities, I mean that the gauge coupling is a function of light cone time. These appear better in the sense that the kinds of problems that happen here do not happen in these kinds of cases because the special properties of these null of these light-like variables. In this case, weak coupling appears consistent. Now, there's a long song and dance here. I'm not going to go into that. But in hindsight, it's perhaps fair to say that generic severe time-dependent deformations on the vacuum state are expected to thermalize on long time scales. In other words, they might be dual to black hole formation in the bulk. So this perhaps suggests that if you want to construct a big crunch, then perhaps you should have something non-generic. So this suggests that perhaps non-generic initial conditions are required for a big crunch, which suggests that the dual CFT state is perhaps non-trivial. Okay. Now there have been further various interesting insights that were uncovered by Engelhardt, Horowitz, Hertog, and various other groups over the years. I won't have much more to say about this. I'm going to put a new spin on this whole thing. New angles on this collection of questions, but these questions I think are important and remain, and it would be nice to understand if this sort of intuition and expectation bears true, and if so, what might be ways to understand big crunch singularities in string theory and holography. If there are any quick questions on this, on just this broad background, it might be good to take them right now. If not, I'll carry on.
Please go ahead.
Yeah. Okay. So in more recent times, we've been seeing over the last actually many years, we've seen that entanglement provides very useful holographic probes. And in the current context, I'd like to explore the behavior of high dimensional extremal surfaces with regard to the big crunch singularity. So in particular, the ADS-Kastner space. So there's a long collection of things that one can do, and one can do it in great detail. And what we end up finding is the following. So firstly, it makes sense to study strip-shaped subsystems in these cases. These are codimension 2 classical RT-HRT surfaces. They're parameterized by these sorts of by 2 functions of this kind, basically. The time dependence basically means that the surface dips into the time direction also besides the radial direction. Okay, and here is the kind of picture that we end up finding. So just to give you a sense of what this is like, let me just zoom into this. What did I just do? So this is the kind of picture that we find. Here is a boundary theory. Here's a boundary space. The singularity is way over here, far above. This is at t equal to 0. Everything I'm thinking of is in terms of a big crunch. Here is the anchoring time slice. So what do we usually do in studying such extremal surfaces? We study surfaces of this kind. We look at boundary subregions of this kind, and if this were a time independent space, here is a constant time slice, and the surface would then lie on this constant time slice. But in this case, there is time dependence in the background, and this time dependence basically forces the extremal surface to bend in the time direction also. Okay, so in particular, an extremal in this case, it's possible to do an explicit analysis of this of the system, and what we find is, why is this not moving? Sorry, yeah. So in the semi-classical region, far from the singularity, it turns out that studying this extremization process is quite reliable, and you can study this in great detail. And what we find is that the surface lies almost on a constant time slice. In other words, there's mild time dependence, but it bends away from the singularity. Okay, so the surface looks like this basically. Okay, so there's mild time dependence and it bends away. So the singularity is somewhere here, and the surface basically bends away. So in some ways, the singularity region appears repulsive in some ways. Okay, so with this in mind, it's interesting to ask, what do quantum extremal surfaces behave like, and whether we and can we get some insight into how these behave in the vicinity of the singularity, and can we probe the singularity region through these sorts of quantum extremal surfaces. In order to study these quantum extremal surfaces, I'm going to take a digression into studying just two-dimensional gravity models and cosmologies. So the last many years, we've seen that there have been various studies of nearly ADS2 holography. We know that extremal black holes and black brains in the near horizon throat regions give an ADS2 cross a transverse space type space-time. If you compactify this transverse space in the IR limit, what you end up with in the IR region, what you end up with is JT gravity plus matter. The action of JT gravity looks like this. Okay. You could ask what happens for more general two-dimensional gravity theories. These can also be shown to arise as two-dimensional subsectors of high-dimensional gravity on spaces like that. Okay, so if you again compactify this transverse space, what you end up with is a generic two-dimensional theory of this kind. Okay. Now the phi here is basically the two-dimensional dilaton, and it basically corresponds to the high-dimensional transverse area. The U of phi is a general dilaton potential. Okay. Now, if U were equal to -2 phi, what you'll end up with is JT gravity, but otherwise you end up with something more general. The kind of reduction ansatz that's at play here is something like this, and this is the two-dimensional space that we are talking about. In addition to compactification on this transverse space, we also carry out a Weyl transformation to absorb the dilaton kinetic terms into the curvature. So this is standard convention in this literature, and that's all I'm employing here. Now there is a sense in which some sort of effective holography is at play here, in the sense that we are focusing on a subset of bulk observables and their duals. We're only focusing on this two-dimensional subsector. And these sorts of generic two-dimensional, if you analyze this in some more detail by looking at specific observables, for example, the suggestion that comes out is that such generic two-dimensional theories are akin to higher dimensional gravity. So they're not near JT, so to speak. So for example, if one looks at the reduction of higher dimensional ADS, for example, what you end up with is a dilaton potential that looks like this. And you can then study observables like the holographic energy momentum tensor or correlation functions and so on. And these reflect the higher dimensional theory. So this we can turn around, and then we can say that this, we can use this to say that we can use a two-dimensional theory as a diagnostic of the higher dimensional theory. Okay. Now, this is only an approximation, the two-dimensional approximation to a fuller theory, and so you might ask that this is just an approximation. It is an approximation, but it turns out to be adequate for some aspects, including entanglement of the kind that I will talk about. Okay. So the kinds of things that one would like to do if one wants to use these two-dimensional dilaton gravity models as interesting playgrounds for a big crunch or a big bang are more complicated. So one technical route that one can take is to look at higher dimensional cosmologies and then do a dimensional reduction to 2 dimensions on the transverse space in this way. So that again specializes to only certain classes of such cosmologies that one can address, but that is still a sufficiently broad class, it turns out. And it turns out that the minimal class of theories that allow such interesting playgrounds is theories of this kind. So this is a 2-dimensional dilaton gravity model with a dilaton potential that couples the 2-dimensional dilaton and an extra scalar. This extra scalar you can think of in certain cases as the analog of the string coupling as a dilaton in higher dimensions. So what we would ordinarily call the string coupling in higher dimensions. So this extra scalar leads to non-trivial dynamics. The dilaton coupling here arises from this reduction of the minimal scalar action in higher dimensions. Okay. Now this is a more complicated theory, and but it can be used for the kinds of things that I'm going to tell you about. So the equations of motion are in detail something like this, and we can cut them down to size. We can actually solve them in great detail, it turns out. But first, there's a simple observation that comes out right away. If one looks near the big crunch singularity, one can show that that there is a universal subsector that seems to emerge. Okay. The universal subsector is something like this. The time dependence of the dilaton and the metric and this extra scalar turns out to be pinned down to be something like this. Okay. You can see this by looking at these equations, the equations of motion, and looking in the vicinity of what you might think is a singularity, and then expecting that the time derivatives are going to be the dominant terms, and then focusing on those. Then you end up with a subset of equations of this kind, and now you can see that the dilaton potential and all asymptotic data has disappeared, and you end up with this universal behavior. Of course, it's universal in the sense that there is a universal form of this kind, but this relation, for example, is between these exponents is something that that is still general. I mean, sort of pins down these exponents, the relation between the exponents, but doesn't pin down the exponents completely. Now, one can do more. One can look at these equations and put in a scaling ansatz of this kind, and then actually just solve the equations. If you stick in a scaling ansatz of this kind, then the equations of motion become basically algebraic equations for these exponents. So given these two-dimensional fields, a higher dimensional cosmology looks like this. Okay. So if you take this sort of scaling ansatz for these two-dimensional fields, what you find, you can of course find the known cosmological solutions that have been known before. So for example, one can show that the isotropic ADS Kastner that I was talking about earlier comes out as one of the solutions. Its two-dimensional form looks like this. Okay, so in the two-dimensional, in terms of the two-dimensional background, this ADS5 Kastner, this ADS D+2 Kastner looks like this. Okay, so it has this form. I'm suppressing certain scales here. Well, in particular the Kastner scale, which will play a role at some point The R here, the capital R here, is the area scale that was there in the high dimensional space. The dilaton, you can see, has this universal behavior that I was saying earlier. And these exponents, you can see, are in fact related in the way I was saying earlier. Okay, but there's also various other families of such cosmological solutions that exist that we found using this two-dimensional formulation that I think were not known before. So these include more non-trivial cosmologies with non-relativistic asymptotics, hyperscaling violating Lipschitz cosmologies, and so on. I won't have much more to say about them, but it's interesting to see that they also exist and they can be found in this way. Now, armed with this two-dimensional formulation of these cosmologies, we'd like to understand what quantum extremal surfaces behave like. So before I go on, any quick questions? This might be good to take. Okay.
Narayan, these solutions you found here in this particular case, are they stable solutions?
Stable meaning?
If I perturb around these solutions, and will they affect the results?
Well, these are not supersymmetric or stable in that sense, if that's what you're asking. They are cosmologies, and that's all that they are. You could ask a question about whether the two-dimensional approximation is good enough and so on, and it would not be good enough if we find that we are hitting the near singularity region in some way. But it turns out that, as you'll see, the two-dimensional approximation ends up being consistent, and you'll for many cases, as you'll see.
Thank you. Let's go ahead.
So there have been exciting recent developments in the black hole information paradox, as we've seen over the last few years. There have been new insights from the generalized entropy and quantum extremal surfaces. We've seen two-dimensional CFT techniques that can be used to adapt the 𝗫𝗁𝗁 formula for the subleading bulk matter contribution to the entanglement entropy. So in particular, the generalized entropy looks like this, and this is the kind of expression I'm going to focus on, and I'm going to say more about this soon. This is the classical area term, and the bulk entropy is this. I'll have more to say about this very soon. One might ask if one can study, if one can gain any insight into Big Bang or Big Crunch singularities from these sorts of tools and ideas that we've seen in the black hole context. Now, at first sight, you might think we expect large linear quantum gravity effects here, and so semi-classical approximations will break down. So do we expect to gain anything? Perhaps studying simple toy models and quantum extremal surfaces as probes will give insight into cosmological singularities, and this is what we end up finding. So we do end up learning some things from these studies. In everything I'm going to say, we'll be mostly studying closed universes. So there are not going to be horizons, and so there's no appreciable entropy. So it's quite unlike the black hole case in that sense. We'll end up taking bulk matter to be in the ground state, which is, you would think, reasonable, far from the singularity. It's then also consistent to say that there's no entanglement with elsewhere. In other words, auxiliary universes that could be regarded as purifying universes for if we were talking about mixed states. Okay, so there are a few more points that come about in this formulation and in the way I'm using them. So here is the generalized entropy. This is the bulk entropy with the curved space effects put in as Almairi and others formulated it. We'd like to, so this delta squared here is a space-time interval between the observer and the quantum extremal surface. The quantum extremal surface is going to be taken at the space-time location r, t, and the observer we're going to focus on is a holographic boundary observer at t0, 0. So the observer is on the boundary at r equal to 0, and it's had a time coordinate t0. So firstly, this generalized entropy pertains to the two-dimensional theory that arises from the dimensional reduction of this high-dimensional space in this formulation. All the subsystems here are necessarily the full space because we've compactified the high-dimensional transverse space. So the quantum extremal surface now is a point in the two-dimensional space, and so this looks like it's the IR limit of the high-dimensional RT surface that I was talking about earlier. We'll take the two-dimensional matter to be approximated as a CFT in the ground state, and you might think this is reasonable far from the singularity. We'll also impose this condition that the central charge of this matter lies between 1 and 1 over G. This basically says that the classical area term is dominant, but S bulk, the bulk entropy term, is appreciable. Now, if the S bulk, if the bulk entropy term overpowers S classical, the classical area, then the Bekenstein bound will be violated, and this might lead to the phenomenon that's been called islands in the formulation of Hartmann and company. Okay. So
5 more minutes.
Yeah, sure. So it's useful to focus on a time-independent example just to get a sense of how this works. So I'm going to just focus on this ADS di plus 2 reduction that I was talking about earlier. The two-dimensional background then is just this. There's no time dependence here, and so the generalized entropy is basically a function of one variable. It's the function of just this variable, the radial coordinate. If you extremize with this, then you can see from this expression here that both these terms, right? Both these terms are negative. They come with the same sign. And so if C is positive and DI is greater than 1, you can see that there's that the only solution here is R star goes to infinity. Both these terms independently have to vanish. This means we end up with the entire Poincare wedge. Okay. So here's a picture of this kind. So this is the boundary, and we end up with this. We end up with R star going to all the way to the to infinity. So you get the entire Poincare wedge. This is what you would call the usual entanglement wedge for ADS2. Okay. And if you analyze this more, you can see that the on-shell entropy, in fact, essentially is vanishingly small. And this is consistent with the fact that this is the ADS ground state. Now, you can recast, it turns out, this expression for the generalized entropy in this form. So you can always recast it as phi plus essentially some constant times log phi. And so you can see that in this case, as long as phi is not too small, the S bulk term is always subleading to the classical area term. And so the Bekenstein bound is not violated and there are no islands. Now, had we appended a region, a flat non-gravitating path region, as is important for black hole studies beyond this ADS boundary, then you would have a modification of this expression, and that turns out to lead to islands. Okay, but that's not going to be physically relevant here because we're talking about closed universes, and it's consistent to talk about this as a universe in itself. So with this intuition, where we can see that for these sorts of cases, we end up with the entire Poincare wedge over here. We look at these cosmologies. So I'm going to look at this ADS2, ADS-D plus 2 Kastner reduction, and the two-dimensional space then looks like this. The two-dimensional diagram looks like this. You might think that the observer, at least if you focus on the semi-classical region far from the singularity, is expected to have mild time dependence. And so this you might think is not going to be too different from ADS. Okay, and if the matter is in the ground state, this is reasonable far from the singularity, you might think that the structure of this quantum extremal surface solutions that we find should be similar. And in fact, this is true. So you can show that, in fact, the quantum extremal surface now lies at the location T star and R star. So T star is the time location of the quantum extremal surface. The observer is at T naught. Mild time dependence basically means that you expect T star is almost T naught. In other words, delta T is small, delta T is steep, T star minus T naught. And you also expect that R star goes to infinity. And the fact that we are in the semi-classical region far from the singularity means that T star is also large. This in fact ends up being true. You can show by an explicit study of these extremization equations that in fact this is true. The quantum extremal surface ends up being driven to the semi-classical region, and the entanglement wedge then therefore excludes the new singularity region. So this figure is of course exaggerated. The singularity is way over there, way in the top. And as the observer marches on, the quantum extremal surface lies here. Okay, since we are driven to the semi-classical region, the two-dimensional cosmology is a reasonable approximation to the higher dimensional cosmology. Now one can regulate the system and ask if you can get more insight, and you can in fact regulate it. So we take R star to be a finite but large boundary of the entanglement wedge effectively. And then you can show that as long as the quantum extremal surface is space-like separated, this lag is always, the quantum extremal surface always lags behind the observer. Okay, so this is the kind of picture we find. So the observer is here, the quantum extremal surface always lags behind them. You can quantify this, and you can also then show that in the presence of a regulator, the quantum extremal surface lag increases as the observer evolves in time. Okay. If you append a time-independent region far from the singularity, as just a toy example, you can this picture confirms the kind of evolution that I'm talking about here. You might ask, are there islands here? And there's a long song and dance. The bottom line turns out to be that, well, the intuition is that you might think that maybe there's something more going on here. Maybe this term flip sign, since we saw that the lag increases, you might think that maybe this term increases, and so this term might flip sign, so you don't get the sum of two positive terms. You get some non-trivial large finite hour quantum extremal surface solution, and a space-like separated island-like region for this window. This turns out to not be true. It turns out. So if you analyze in detail, expanding near this island boundary, you can show that there's inconsistencies and there's no island-like solution that emerges continuously from the quantum extremal surface in the semi-classical region. So this turns out to be consistent with previous studies of closed universes with no horizons, no entanglement with elsewhere, and no flat non-gravitating path regions. But it's still curious that and technically interesting that this is true. So you can also show that more general two-dimensional cosmologies also exhibit very similar behavior, which then you might think begs the question of whether this is general. Is this always the way it's going to be? It turns out that that's not always the case. There are other cosmologies where something more happens, it turns out. I mean, something qualitatively different happens, it turns out. So if one looks at null Kastner singularities, so these are essentially singularities are essentially cosmologies where there's only X plus dependence, and so there's some sort of holomorphic structure that emerges. Okay, so everything here is only a function of X plus, where X plus is this combination. The dilaton here is this, and the extra scalar I was talking about is that. Since there's this holomorphic structure, you can recast the two-dimensional metric in flat variables, and that's what I've done. And now what you find is something somewhat different. Okay, so the equation of motion boils down. The equations of motion boil down to a single equation, a single non-trivial relation between these two scalars, and so there's a whole function worth of such solutions you can find. And in particular, if one looks for a big crunch like like solution, then in fact what you find is something like this. And you can now analyze the generalized entropy. And you can again see from the generalized entropy that in fact there's a decoupling. You can see that there's a decoupling between the X plus and X minus sectors. This is the result of this holomorphic structure that comes out. And now you can again see that as long as you look for space-like separated quantum extremal surface, and it's consistent to do that. And there are in fact non-trivial solutions. What is remarkable is that the quantum extremal surface ends up lying towards the singularity. So the observers here, the singularity is over here at this slice, at this null slice. The quantum extremal surface, unlike the previous cases where it was repelled from the near singularity region, here it lies towards the singularity region. So in particular, from this relation, you can also see that in fact X plus equal to 0 is in fact a solution when the observer X plus 0 is also 0. In other words, the entanglement wedge can potentially include the near singularity region. At least that's what this suggests. Okay. On the other hand, of course, at this level, if you analyze the on-shell generalized entropy, you can show, of course, that this appears singular generically. So you might think at this level, at the near singularity region is still best regarded as unreliable. And it's perhaps consistent with the fact that strings are known to become highly excited in the vicinity of such null singularities. But I think there's more here, and maybe one can do more by analyzing the structure in a bigger way and so on. So I'm going to stop, and I'll just leave you with these conclusions. So we saw that for the ADS-Kastner case, the classical RT-HRT surfaces anchored in the reliable semi-classical region bend away from the singularity. The quantum extremal surfaces are also driven to the semi-classical region. For null Kastner singularities, there's something qualitatively different that seems to be happening. Quantum extremal surfaces now can reach the singularity, but the on-shell generalized entropy appears nevertheless generically singular. You might ask, we've been using this reasonable intuition that we start off with ground state bulk matter far from the singularity and then extrapolate and then look for extremization within. Maybe one should be looking at appropriate non-ground state models for the bulk matter entropy. And this might then perhaps be consistent with this question about what the initial conditions are in the semi-classical region far from the singularity. And possibly non-trivial, non-generic dual CFT states. You might more broadly ask whether you might ask more broadly about which big crunch singularities are accessible via entanglement of this kind. There are further new structures that emerge when one studies de Sitter and de Sitter-like spaces. What we find is time-like separated quantum extremal surfaces generically. And this suggests that perhaps, and if you look at the classical study, if you look at classical extremal surface in de Sitter, it again suggests that perhaps something new is going on. So I'm going to stop here and I'll leave you with these thoughts. Thank you.
Thank you, Narayan, for an interesting talk. We have very little time for some short questions. I think Harvendra has put up his hand. Harvendra, please go ahead with your question.
Yeah. Hello.
Yeah.
You can hear me? Yeah. Okay.
Yeah.
Yeah. Okay. So very nice talk, Narayan. I have a very short question. Your Krishnan geometries, is there time symmetric there? Is that t going to minus t if I take?
Yeah. So everything I'm saying is on one side of the singularity. So you see, so what I'm calling t here is really is really here. I mean, so the singularity is over here. I'm going to approach everything from one side of the singularity, and so what I'm calling t here, you can think of as mod t in some ways, if you like.
Usually it is mod t, so one can actually think of something after t equal to 0 also in your case. That is my question. Yeah.
Sorry, repeat that please. I couldn't get the last part.
No, I am saying that usually there is a mod t there in the Krishnan geometry, so you can take t2 minus t and then draw the these surfaces beyond t equal to 0 also. Yeah,
but I think the physical question would be to ask how you go from one side to the other, and so that's the sense in which I'm saying that if you focus on just one side, you find that the near singularity region already looks difficult to approach.
Yeah. Okay, I understand.
Yeah. Something, you have a question, please go ahead.
Yeah, Narayan, thanks for a nice talk. I can ask you this also later, but do you know of examples, let's say we reduce to 2 dimensions, like I think you were doing in some cases, where you have a classical singularity in the classical theory, you couple in matter and include the quantum back reaction, and because of the violations of some energy conditions, the singularity gets resolved in a controlled way, in a cosmological setting? Because I haven't been able to find such an example.
No, I haven't either. In fact, you may remember that in that old time when we were looking at these null singularities, also we were trying to do something like that. We were trying to ask if we could find bounce-like solutions, for example. And in this model, in this two-dimensional context, also I can't seem to find that. But I don't see any reason that they cannot be. So maybe one should revisit those questions again. Is my first reaction.
Okay, well, you can actually, so what we find is you do get bouncing geometries. This is tied to what I was telling in the talk after Tadashi, but you have to go beyond the semi-classical regime of keeping gravity classical. When you quantize the full gravity theory, you can, but not in this kind of semi-classical way.
Right, right.
Okay.
That's interesting, I see.
Yeah, no, but thank you. We'll chat more. Thanks.
Narayan, I have one question.
Yeah.
So all this two-dimensional theory extra you derive from a higher dimension, possibly we assume that the higher dimension theory didn't have a dilaton. But suppose I had the higher dimension theory a dilaton, could have found the solution where also the dilaton potential will also would have been vanished.
So in this catalog of these solutions that we had, one can look at, so when I'm looking for a reduction like this, I'm looking for a two-dimensional formulation. I require in some ways that this transfer space can be reduced on. Now, of course, you can relax that and do multiple reductions, so to speak. You can you can look at an anisotropic space, for example, here, and do a partial reduction on one subspace, and then do a and then do a further reduction on the other subspace, and so on and so forth. That would then lead to two-dimensional theories which are multiple scalars, which would be like the multiple warp factors for those multiple internal directions, so to speak. And presumably this sort of thing can be done then. I've just focused here on the simplest case where I look at one such. I mean, the minimal content where we have one scalar, so to speak, that comes out here, so to speak. Now, of course, so in particular, for example, even in this Kastner family, there's there are the generic system is a fully anisotropic Kastner system, and one of the examples, for example, has this vanishing dilaton potential. It's flat space, and it's basically the reduction of mostly isotropic Kastner. But you could do what I was just saying earlier to do sequential reductions and
identification might be different.
So I'm not sure how much more I can do with them, but I think it might be interesting to see what you get. I don't know. I didn't have any obvious nothing to say.
Okay, thank you very much for talk. Are there any other questions? I believe we are running short of time. There are no questions, so in that case, let's thank Narayan again. Zahed, are you there?
Yes. Can you hear me?
Please put on share your screen. Yeah. So our next speaker is Zahed, and he will be talking on crossing symmetric dispersion relations in quantum field theories and conformal field theories. And so, Zahed, please.
Yes.
You will have to. I will remind you after 20 minutes. You have to wrap up in 25 minutes. Then there will be 5 minutes discussion.
Okay, thank you. Thank you everyone for being here, and thank you the organizers. So I'll be talking about crossing symmetric dispersion relations in quantum field theories and conformal field theories. So this talk is based on these three works with Anindo, Rajesh, and Parthiv. So now, so dispersion relations are basically a non-perturbative representation of scattering amplitude. So in order to write down a dispersion relations, people usually fix one of the Mandel-Steam invariants, and then usually people fix T and then write a complex integral in the S variables. So in our examples, we will consider 2-to-2 scattering of identical particles. But drawback of writing a fixed T dispersion relation or fixed S dispersion relation is that crossing symmetry will be missing in one of the channels. But from the Feynman diagrams, and we know that Feynman diagrams have inbuilt crossing symmetry. For example, if you consider 2-to-2 theory. And so why we'll ask the question that why should not we start with a non-perturbative representation that is crossing symmetry itself. So yet in last 50 years, people have been more focusing on this fixed dispersion relations. A crossing symmetric version of the dispersion relations first written down by Aversion and Curie. When we got this paper, when we first saw this paper, it had only 9 or 10 citations, even though it is dated back to 1972. Now, so in our talk, most of the cases will be seeing this kind of expansion. So let's see. So amplitude, the 4.22 scattering amplitudes is fully crossing symmetric. So it can be expanded in powers of crossing symmetric variables, this x and y. X is the crossing symmetric quadratic Mandel-Steam invariants, and y is the cubic combination of the Mandel-Steam invariants. And this WPQ are the Wilson coefficients. So this Wilson coefficient actually appears in the low energy expansion of the Lagrangian. So this WPQ actually appears in front of the higher dimensional operators. So let's here is the outline of my talk. So first I'll say how to write down a dispersion relations which will be crossing symmetric. Then we'll write down an inversion formula for the Wilson coefficients, and we'll write down some rules. And from the inversion formula of the Wilson coefficients, we'll derive some positivity bounds, positivity inequalities for the Wilson coefficients. From there, we'll bound the effective field theories. And after that, we'll move to the geometric function theory of the amplitude. So we'll ask the question that these Wilson coefficients are two-sided bounded. So why this two-sided bounds exist? Which properties of the amplitude actually give rise to this two-sided bounds on the Wilson coefficients? So we'll see that this emerges as a consequence of geometric function theory. Now, after that, we'll see that this crossing symmetric block expansion, crossing symmetric dispersion relation gives us a very rigorous derivation of the crossing symmetric block expansion or routine block expansion of the 𝗲𝗂𝗶 bootstrap. So let's begin. So to write down a crossing symmetric dispersion relation, one have to parameterize the Mendel-Stem invariance, the S and T, in terms of the parameters Z and A. So this parameterization is given by this formula. So this red box. So this S are the shifted Mendel, SI are the SK are the shifted Mendel-Stem invariants. So S1 is basically S minus 𝜇/3, and S2, S3 are basically shifted Mendel-Stem variables by 𝜇/3, where 𝜇 is 4n square. And this A and Z are the crossing symmetric variables, and ZK is the cube roots of unity, and A is given by this formula. So quadratic combination of the Mendel-Stem variables and divided by cubic. Now, using this parameterization, if you try to recognize the image of the physical cars, then it turns out that this physical image of the physical cars actually maps to this unit circle in the complex Z plane. So in order to write down a crossing symmetric dispersion relation, we can fix the A and write a complex integral in the Z variables. And after that, you can transform that dispersion relation in terms of Mendel-Stem invariance. And the form of the dispersion relation look like this. So this alpha naught is the subtraction constant, and this A is the imaginary part of the amplitude or absorptive part of the amplitude, and this H is the kernel of the integration, and S1 prime is the integration variable. And you know that second argument of the imaginary part of the amplitude is actually given by this formula, and this S2 plus is basically a function of S1 prime. This is the integration variable, and the A is given by this formula. So A is fully crossing symmetric. So this shows that this representation is fully crossing symmetric, and this is a Regge bounded in all three channels. Now, from the dispersion relation, if we put the partial wave expansion of the channel discontinuity, this is basically look like this, and we can get a block expansion of the amplitude, which is fully crossing symmetric as well as Regge bounded. So, but the point is that this block expansion has some non-local terms. In the next slide, we'll see what are these non-local terms. But one have to remove these non-local terms to make the amplitude local and fully crossing symmetric and Regge bounded in all three channels. And this is so if you from this Dyson block, from this expansion, from this Dyson block, if you remove these non-local terms, then you get a Feynman block expansion. Now, as we have seen earlier, that completely crossing symmetric amplitude has expansion in powers of x and y. And from the dispersion relation and from the Dyson block expansion, you can write down a inversion formula for this Wilson coefficients WTQ. An inversion formula look like this. So now you can see that for this inversion formula, if you put m greater than n, so this first argument of this dark blue becomes negative. So, but from this integral expression, it's not clear that it will be negative by trivial. So this will put a very non-trivial constraints on this partial coefficients. These are basically called the null constraints, and they put very non-trivial constraints on the partial coefficients. Now, from the inversion formula, from the positivity of the Gegenwarp polynomial, and also using the unitarity, that means the positivity of the partial coefficients, one can derive this inequality. So these chi's are basically some known functions. These are given by this. These are very simple functions. And let's see how important this inequality is. So in the case of effective field theory, people usually know some low energy expansion of the amplitude, some low energy values of the amplitude, or the low energy Lagrangian. So from there you can compute some low W's. So for example, if you are given W10 and W01, which are the coefficient of Ax and Y, so then we ask the question that if such terms are given, let's say we consider an example as a 4-dilaton and closed-string superstring T amplitude with a subtracted out massless pole contribution. So let's say that for this amplitude, we are only given this first two terms, W10 and W01. So we ask now that why the first massive string pole should occur. So now if you plug this value in this inequality, you'll see that the first massive string pole should occur below 1.07. And if you consider higher Wilson coefficients, you'll see that fast massive string pole that value will converge to 1. So this inequality basically puts very non-trivial constraints on the Wilson coefficients. So now from the null constraints, one can actually bounce the cross section as well. So this cross section formula for this cross section is given by this. We truncate the spin sum up to Lmax, and these are the bounds. So this blue line is the Lmax equals to 36, yellow line is Lmax equals to 46, and green line is Lmax equals to 60. So you can see that this is converging. And this black dotted line is the Fawcett bound. So this high energy Fawcett bound. And our bound actually numerical Fawcett bound, but it valid for all energies. You can see that pi and bootstrap. So these red regions are the pi and bootstrap values of the cross sections, some pi and bootstrap amplitudes. And you can see that this cross section actually lies far below the bounds that we have obtained. So now let's see how geometric function theory and amplitude are related. So now we have seen earlier that the amplitude has a crossing symmetric expansion in powers of x and y, and our ax is the quadratic crossing symmetric combination of the Mendel-Stem invariants, and y is the cubic combinations. So these W's are the Wilson coefficients. They sit in front of the higher order, higher dimensional operators. And this works by these guys. They have shown that that Wilson coefficients are basically two-sided bounded. So this ratio of WPQ by W10, these are basically bounded from above and below. And this N1, N2 are order 1 numbers. So now we ask the question that why this kind of bound should exist. So which properties of the amplitude actually responsible for this kind of bounds? So we answer this question from this famous formula conjectured by 𝗵𝗶𝗿 and then later proved by de Bruijns. Now let's see what is this 𝗵𝗶𝗿 conjecture is. So 𝗵𝗶𝗿 conjecture actually tells us that how fast a Taylor coefficient of a holomorphic univalent function can grow. So let's say f of z is a univalent function and it has a Taylor expansion of this kind. And coefficient of z is, we have put this to be 1, and this other Taylor coefficients bp. So 𝗵𝗶𝗿 conjecture tells us that this bn or absolute values of this bn should be bounded by n for n greater than equals to 2. And if a function is univalent, then it shows that the absolute value of the function itself is two-sided bounded. So an univalent function is a function on a domain if it is a holomorphic and one-to-one. So now let's see how. Okay, so now as we have seen that earlier, that amplitude has a fully crossing symmetric expansion in powers of x and y, and this w's are the Wilson coefficients. Now using our parametrization of Mendel-Stem invariants in terms of z and a, we can write down the formula for x and y. So they are basically given by these formulas, and a is given by x and y, x by y, y by x, and z tilde is basically z cube. That z cube that appeared in our parametrization of S1, S2, S3 in terms of z and a. So and now we can now our amplitude is function of the function of z tilde and a. Now we can expand this amplitude around z tilde equals to 0. and the expansion is look like this, and this alpha n a to the power 2n is basically related to the Wilson coefficients, and the formula is given by this. Now let's see how this is related to the quantum field theories. So this is the crossing symmetric dispersion relation we have seen earlier. So this A is the
5 more minutes to wrap up.
Yeah. So this A is the channel discontinuity, H is the kernel. One can show that the H is basically a univalent function from this information, and from the unitarity, basically one can show that the coefficients, this alpha n's by alpha 1 is basically two-sided bound. Alpha 1 are basically ratio of this absolute value of that this guys is basically bounded by n for n greater than equals to 1. And also one can show that amplitude also bounded from above and below. And for a small a, from the argument of unitarity, one can show that this combination is also univalent. This amplitude is also univalent. Now from n equals to 2 conditions, we get that from this Weber-Beck n equals to 2 conditions, we get that this ratio W01 by W10 is basically bounded by these regions. So you remember that these are the first two expansion coefficients, and these are the bounds. So these dashed lines are the bounds, and this all the dot are the values from the S matrices that is obtained from S matrix bootstrap. These values actually you can see that they are actually satisfy the bounds. So there's a work by Anindya Prasad shows that the amplitudes are typically real functions, and they established a more tighter bounds on the Wilson coefficients from the theory of typically real invariant functions. So this is the lower bounds and this is the upper bounds, and you can see the first row is the first column is the from the typically real invariant function, and this one is HDPP results. And you can see that some of the values are basically stronger than the SDPP results. And from these bounds, from the Weber-Beck conjecture, one can show that this theory space is bounded. And this W and this WPQs can't grow orbitally. So you remember that here they're computing WPQ by W10. So they're choosing the normalization that W10 is basically 1. So in this recent work, we have also shown that this fascinating corresponding between this geometric function theory and scattering amplitudes basically holds for even ON global symmetry using fully crossing symmetric dispersion reactions. So we derived two-sided bounds on the Taylor coefficients around crossing symmetric point, and we see that this CPQ are two-sided bounds. So here is some bounds. And from here, we also shown that this theory space can be arbitrary. So this CPQ are bounded, and these dots are various S matrices amplitude that one got from S matrix bootstrap. They actually satisfy these bounds. So now we'll see how we'll see our application of this dispersion relations in the context of conformal field theories in Miller space. So one of the main object of interest is the calculation of the critical exponents. So one of the way to calculate the critical exponents is the conformal bootstrap, and fully crossing symmetric bootstrap seems to be more elegant and promising way to determine the critical exponents. So this fully crossing symmetric approach was first proposed by Polyakov in 1974, and then this was further developed in Mellin space by Gopakumar, Koviraj Sen, and Sinha. This approach currently lacks a non-perturbative derivation for d greater than equals to 2. So crossing symmetric dispersion relation actually provides a rigorous derivation of this fully crossing symmetric bootstrap approach. So now here is the convention. So 4-point correlation function has a Mellin amplitude of this kind. So this Mellin amplitude, this M is the Mellin amplitude, and this gamma factors we have factored out for convenience. We'll write down a dispersion relation for this Mellin amplitudes. And this Mellin amplitude has a partial expansion, and from the partial wave expansion, one can write down the channel discontinuity, and one can plug this channel discontinuity in the crossing symmetric dispersion relation, and one gets the crossing symmetric, fully crossing symmetric and Regge bounded block expansion of the amplitude. This is called this we call the 𝗲𝘂𝗶𝗿 block. This is fully crossing symmetric and Regge bounded. Now, as we have seen that the 𝗲𝘂𝗶𝗿 block has a non-local terms for this WPQ, Wn minus m comma m for m greater than n. So these are basically non-local terms. One have to remove this non-local terms from the 𝗲𝘂𝗶𝗿 block. If we remove this non-local terms from the 𝗲𝘂𝗶𝗿 block, you get a expansion of this kind. So for these terms are the S plus ST and U channel Witten diagrams, and these are basically contact terms. So this is we call the Witten block expansion. This is fully crossing symmetric, local, and Regge bounded in all three channels. Now, in order to put constraints on the safety spectrum, these are the conditions that you have to apply. So one of them, first of them is the 𝗲𝘂𝗶 conditions. So the amplitude should vanish at S1 equals to delta phi by 3 plus P for any S2, and P is integer. And also amplitude, this should have satisfied this null constraints. And this puts very non-trivial constraint on the safety spectrum. Now, it can be shown that from the fixed the sum rules that one get from the fixed dispersion sum rules, those are got by these peoples and can be recovered from this 𝗲𝘂𝗶 conditions and the null constraints. So we'll see. So in the right hand side, left hand side, you can see this fixed dispersive sum rules, and the right hand side, these are the crossing symmetric dispersive sum rules. We can Taylor expand these guys around S2 equals to 0. And the Taylor coefficients, small omega r and capital omega r, they are basically related by null constraints. So basically it says that fixed dispersive sum rules equals to crossing symmetric dispersive sum rules plus combinations of null constraints.
Please summarize.
Yes, here is the summary of our results. So we derive the inversion formula and sum rules. We derive positivity bounds, that positivity conditions that constrain the effective field theories. And we have shown that the two-sided bounds on the Wilson coefficients emerges as a consequence of geometric function theory of the amplitudes, and we give a rigorous derivation of the crossing symmetric block expansion or 𝗲𝘂𝗶 block, Witten block expansion of the 𝗲𝘂𝗶 Milne bootstrap. So here are some future directions, and so these formalisms can be extended to external spinning particles. So there is ongoing work by 𝗏𝗵𝗶𝗿, Kaushik, Parthiv, Prasad, and Anindhu. And in the discussion sessions, there will be further discussions on the issues related to this axiomatic dispersion relation by Gyan Maharana. So if you are interested, then be present there. So thank you.
Okay, thank you, Guy, for a very extensive and interesting talk. Are there questions? Very short questions because we are. Okay, Alok has raised a question. Alok, go ahead.
Hi, yeah, just a small question. So this crossing symmetric dispersion relation, I mean, sorry, I missed. What are the assumptions in the sense that in the usual fixed dispersion relation, we need the polynomial boundedness and the analyticity, right? In S for fixed. Yes. So is that enough to derive this, or
yes, that is enough. That is enough.
I see. But because in that case, if you look at nuclear scattering, like we know that you won't have crossing symmetry, right? I mean, the things like 𝗵𝗶𝗿 theorem will be violated for some. I mean, the dispersion relations are not valid for certain processes, right? The fixed dispersion relations.
Yeah. So assumptions that here goes is that basically it's a polynomial bounded and it's crossing symmetric. That's all.
Crossing symmetric. I see.
Yeah, that's all. Yeah, you don't need anything.
But is that equivalent to? Sorry, but is that equivalent to the, analyticity in S for fixed T and the analyticity in T for physical S? Is that same, or is it more than?
No, this is actually the same. The same thing.
Okay. Thanks.
You are just parameterizing the S and T in terms of Z and A. That's all.
I see. Okay. And in the older days, people used to say that for complex S and T, behavior of the amplitude was not clearly known, right? It was only known for, and you keep one thing physical, and so that's why.
So this parameterization actually these are basically the same thing as that you consider in the fixed dispersion.
Okay. Thank you.
Okay. Are there any more questions? Well, if not, no, sorry, Siraj, please go ahead.
Hi. Thanks for the very nice talk. when you use these your dispersion relations to constrain Wilson coefficients,
Yes.
Do you get new relations that you would not have got if you were using just the ordinary dispersion relations, or is it basically a matter of convenience that makes it easier to use these?
So yeah, this kind of bounds that you can. So these are basically this 𝗵𝗶𝗶𝗿 structure. This amplitude is basically a typically real invariant function. This structure actually doesn't emerge from the fixed dispersion relation. You can't show that. So as far as we know. But this kind of bounds actually exist. So one can show that from the fixed dispersion relation, you can show this kind of bounds. But from here, this typically real invariant function, you actually get. So those calculations are basically numerical, and our bounds are basically more tighter than those bounds.
So I didn't understand. Is it a matter of convenience? I mean, is it the same information is there in both, or there's more information here? It's just that it's easier to use these relations, or there's more information?
No, so information is the same. Same information is there. Yeah.
And right at the beginning, you said something was not visible in that. I missed your word. What did you?
So yeah, this typical. So this amplitude. So if you write a crossing symmetric dispersion relation,
yes,
from there you can easily show that this amplitude is for certain range of A. This amplitude as a function of Z is a typically real function.
No, I think he's asking something different. He's asking that in the fixed T dispersion relation, crossing symmetry wasn't manifest. So I think that's what he is asking here.
Oh, I see. So yeah.
Is that what you're asking, Shiraj?
No, so it's not a very clear question, Anindya. I was asking whether there was something, some structural feature that comes out here that you could not see from that other thing easily, or yeah.
Yeah. So the fact that you have crossing symmetric partial waves, the partial waves that we have in the fixed dispersion relations are not crossing symmetric. So here you have the structure that you have some exchanges and contact diagrams at each order in the partial wave expansion.
Right. Okay, thank you. One quick other question. To get your bounds, you assumed the absence of cuts. Is this right?
No.
The thing that he has described is actually for the massive pions, or where there are cuts from s equal to 4m² to infinity.
I see. And how did you deal with those? How did you deal with those cuts?
Yeah, so he had a picture. So go back to that picture where the z plane, the cuts are there. So
So we basically write down a complex integral interior to this. So from this parameterization, you can see that physical curves actually map to this circle, and we write down a complex integral inside and outside this circle, and make them go towards the circle, unit circle.
Yeah, that's how you pick up the absorptive part instead of the.
Yeah, that's how you get this.
Cuts start only at much higher energies than the process you're interested in.
In the thing that he has described, yes, because he's describing pion scattering. So pion scattering, the lower limit of the integral starts from the lower limit of the cut. But there are two S-channel cuts, one on the right and one on the left. They don't join up. So, but if we were describing effective field theory or say weakly coupled gravity, then the cuts would join up, and then you would actually start your dispersive integral at some very higher energy scales, like what you have in mind.
Okay. So, I'll ask more in the discussion section. Okay, thank you.
Great, thanks.
Any more questions in one heads? Okay, if not, let's thank Zahed again and for this interesting and extensive talk. I will thank all the speakers of this session, and the technical session is over. Now it's up to Alok and others to take care of the discussion session.
All right, thanks. Thank you so much. So I think we can dive right into the discussion session, and I think Professor Maharana can take over from here.
Yeah, Alok, so what is the upper bound?
It's a tough question. We are perhaps
Sunday evening, okay?
Right. Maybe half hour. I mean, it was supposed to end at 6:30. We already past 6. So will 30 minutes, so maybe 40 if stretched suffice?
Okay, so you use the guillotine.
No. I am horrible. My kids don't listen to me. I mean, how the heck am I gonna?
things might get get prolonged. Okay, so
yeah, I would just give you a tinkle. I mean that okay, we can
order of 40 minutes.
Okay,
right?
Very good.
So
Sunil has put up his hand. He wants to talk something.
Who?
Sunil.
Oh, so he wants to only talk at the end, right?
No, I had a question. I don't know, when you're throwing it open for questions, then I have a question for one of the speakers. Usually we discuss, we allow questions for speakers, or we don't have that.
Okay, so Sunil, I thought that I suggest the following, because I thought the people who have been participating, they had very little chance to comment. Okay, so I will suggest the people who are participants, they might make a comment on somebody's lecture, and then the speaker might respond. Because if it be a question answer, I have some 9 speakers. Okay, 2 questions each, and you can imagine how long it will go. So how do people like this idea?
I didn't completely understand. You're allowing comments, but not questions. Is that it? There's not really an invariant distinction between comments and questions. But if you have a bunch of people asking questions, you can start with them, and I'll come in later. That's not a problem.
No. What I was suggesting, there are several topics. Okay, on one topic, okay, there have been 2-3 talks. So I was suggesting that actually let there be some comments, and then the speakers can respond instead of asking individual speakers individual questions.
Okay.
Is it acceptable, or we go by conventional?
Sure. No problem.
Okay, so this is one. So as you can see, there have been diverse topics. So this is not a theme-based day. Okay, so I was thinking, but then maybe I should not do it. I was thinking to say a few words about this dispersion relation and analyticity. Is it okay, or what do people say?
Yeah, please go ahead, please.
Okay. So I'll spend 5-7 minutes on the classical results, in the sense the way analyticity was proved, let us say 60 years ago. So that was based on the LSZ formulation of field theory, which actually assumes vacuum and operators of self-adjoint and microcausality, and then plus the LSZ assumptions like asymptotic fields, interacting fields, interpolation, and so on. So based on that, I'll just tell you the results. So if you take equal mass particles of mass m, then since all the masses are physical in LSZ, so there is a cut, right-hand cut starting at s is equal to 4m square, and there is a left-hand cut starting at u is equal to 4m square. But s plus t plus u is equal to 4m square. So in the s plane, you can say that there is a right-hand cut and left-hand cut. Now, what is proved is fixed T dispersion relation for T, not any arbitrary value of T, for physical T which is negative, but lying within Lemon-Martin ellipse, which is a small ellipse. So you can only prove that the scattering amplitude is analytic in S for fixed value of T. So you can write a dispersion relation, which is actually the amplitude is related to integral over ds for the imaginary part of the scattering amplitude. This is one. Second, which you can show as much rigor as you like, that the amplitude, this amplitude, the mod of this amplitude is bounded by a polynomial in S. This is called the polynomial boundedness. In fact, you can prove a little bit more. This is actually due to Jean or Martin, that the amplitude is bounded by, at most, it will need 2 subtractions. Okay. So therefore, you can write fixed T dispersion relation with finite number of subtractions. Okay, as he pointed out, this is not crossing symmetric. Okay, because you have the S channel discontinuity and U channel discontinuity. But based on that, actually, you can derive what is called the Frossa bound, that the cross section cannot grow faster than log S square. Okay, so this recently has become a little bit relevant in the context of conformal field theories, because in conformal field theory, you don't have a scattering amplitude. Okay? You cannot put particles on and so on. So this is correlation functions, or actually the Weightman functions. So to prove, and crossing can be proved in LSZ rigorously. Okay, really, you can prove crossing rigorously. This is Bross, Epstein, and Glaser. But in case of conformal field theory, it is the Weightman functions. So it is a lot more harder to prove crossing in the sense that you can analytically continue one Weightman function to another permuted one. Take, for example, 3-point function. There are 6 Weightman functions. Okay, I think, to best of my knowledge, this has not really been rigorously proved as in case of quantum field theory. And now people are beginning to explore these things. So I think I'll stop here unless somebody has any question. Now, I sort of now invite comments. Comments, questions. But when you ask a question, please mention the name of the speaker whom you are asking.
Sunil has his hands raised. Sunil Alok.
Okay. Gautam wants to ask a question.
No, I don't want to ask a question. I'm just saying Sunil has his hand raised. Alok has his hand raised. Survi has his hand raised.
Yes, Sunil, yes.
Yeah, my question was for Rajesh, also any of his collaborators or anyone who wants to comment. You know, a little bit, again, I wanted to sort of ask something related to what I asked in the morning. Rajesh, are you there? Or Rajesh is not?
No, I'm here.
Oh, he's there. Okay. Yeah. So, you know, when you say free Yang-Mills theory, I'm always confused by one thing. So literally, if we take G Yang-Mills to 0, then it just falls apart into n copies of free Maxwell theory. No sign of the non-abelian structure constants is there. Is that what the limit means? Or is there some memory in this limit? Is the limit subtle in such a way that the non-abelian nature is still there on that side?
Yeah, because you have to impose the Gauss law constraint still, even as G Yang-Mills goes to 0. So in that sense, it is not just a sum of free.
So it's the non-abelian Gauss law constraint.
Yes.
Okay. Thank you. That's very nice. The second question is, if G string goes to 0 and G string N, that is 't Hooft coupling, also goes to 0, that's where you're in the side of free string theory. The free, free string theory, I guess.
I mean, free in the sense that it's the quantum, it's tree-level string theory.
Yes. Yeah, tree-level, sorry, classical, I meant, yeah. Now, in this limit, we were talking in the morning about the Ramon flux that in Green-Schwarz formalism is normally there in the world sheet theory. So you said something like it formally goes to 0 because it's proportional to GSN, but also, you know, it's there somehow to stabilize the background. So I was wondering if you can sort of elaborate, and in particular, is there some limit, some quantity between GS and N which is kept finite, because GSN is going to 0, N is going to infinity. So is there some speed at which GS is going to 0? That's maybe related to the question.
GS to 0, and I mean, normally you would take GS to 0 and N to infinity such that GSN takes a fixed value. Right. Now, in some sense, that fixed value, you're then further taking to 0. So in some ways, GS is going faster to 0 than N is going to infinity, but not necessarily parametrically. I think just that combination is going to 0. So yeah, so in some ways it's a theory with no free parameters, and at that point there is so this is why the free theory at n goes to infinity, you have an infinite spectrum. Things are spaced of order 1. There's a spectrum, conformal dimensions, which are all spaced in integer spacing, and that's all. There isn't any scale at that point. But of course, yeah. Was that your question?
That was sort of the question, but I was just wondering, we could take any, in principle, you can take any limit of 2 parameters and ask what is the resulting theory. In worst case, it would be uninteresting. But what if you take, say, G string times some power of n to be fixed? Does that contradict any of the limits you've taken? The G string n squared is fixed.
G string, G string n square is fixed is the same as saying that G string is going like 1 over root n, right?
No, 1 over n squared.
Sorry, 1 over n square.
Yeah,
so
a different limit.
I don't know whether there's anything particularly good in that parametric limit as such, which at least I am not aware of anything. You don't want to do the other way around where G string n blows up, but
no, G string n has to go to 0. So I was just trying to understand. Of course, the conventional wisdom is G string n is held fixed, and then the fixed number is taken to 0 as a new independent parameter. Yeah, so that's what you said. I'm just wondering if we take other double scale limits. The things that you developed, are they applicable to those limits also? Because then there would be a parameter. Just trying to understand the whole parameter space of this.
Yeah, I think in the limit, it would just be the same free Yang-Mills as far as I can think. And I don't know whether that parameter really would enter into anything, because perturbative field theory you have under control. So you can do it for small Toft coupling. You can do perturbative Yang-Mills for small Toft coupling. Small Toft coupling in your language corresponds to lambda over n. So you have some lambda tilde, which is G string n square, which will be something, whatever, lambda square over n, I guess, the conventional lambda square over n. Now, perturbation theory, you organize in the large n limit.
Actually, it would be conventional lambda squared over GS.
Sorry, no, I'm just thinking in terms of the Yang-Mills theory. So Yang-Mills theory has 2 parameters, lambda and n. And let me call what you said GS n square is lambda tilde.
That would be lambda, that would be lambda n or lambda squared over.
You could think of that as I think you want to think of that as lambda tilde times lambda tilde is usual lambda times n.
Right.
So keeping lambda tilde finite is not something in G-string Yang-Mills perturbation theory. You wouldn't have anything meaningful, I think, in that perturbation theory. The Toft limit is the limit which has a meaningful perturbative expansion, where you organize things by
by double line diagrams.
Yeah.
I see. Okay. Thanks. I think that's quite.
So should I ask Souvik? Souvik has raised his hand.
I think Surbi was ahead of me. Yeah, maybe she should go first.
Okay. So please go ahead, Surbi.
Yeah, hi. My question is for Professor Arnab Kundu. So basically, I wanted to ask him to elaborate a little bit more on the comments he made in the end about the relation of the OTOC to the growth of local operators.
Okay. First of all, okay, that was really a comment. I don't have anything very precise to say, in the sense that let me think just for a moment. It's not obvious that there is a clear relation that you can write down in terms of linking operator growth with OTOC, or for that matter any correlator, for example. So so the reason simply is that, I mean, well, first of all, there are multiple notions of operator growth, but if you take the most conventional sense, most conservative one, which is basically in terms of how a local operator grows in the Hilbert space of operators, for example. Okay. This Krylov notion, for example, which which in the lattice community have been used for a long time without talking in terms of this language. What you compute are given a local operator, essentially some nested commutators with the Hamiltonian. Okay. So it's a very specific commutator that you are computing. But my comment was really loose in the sense that okay, so let me put it this way. So what happens, or the connections that people can make with, for example, quantities like how fast information is propagating, or a local operator is spreading, etc. They are usually done. They can be connected to correlators, provided you choose very specific operators with which you want to connect. So, for example, you can take one of your operators. You compute OTOC or not, it doesn't matter. Suppose you compute some 4-point function or some higher point function. In that higher point function, you take one of your operators to be the density matrix itself, for example. That would be a very extreme choice. Okay. But if you make such a choice, or a special choice, but if you make such a choice, then there are connections you can draw. So, but I have to think about it. I don't want to say that you cannot, you probably can, but I'm not aware of an immediate connection that you can draw. But perhaps you could.
Sorry, can I just comment on this?
Can I just ask one question first? Sorry. So is this rho? I mean, the 4-point function you said, is it like a 4-point function of rho, density matrix, and
no. So what you do is typically you take, let's say, for example, you take one of the operator to be the density matrix, and then you take other two operators as some light operators that you have in the spectrum.
Okay.
So then, I mean, for example, this method that I mentioned very impressionistically about the mean field approach of computing higher point correlators. Essentially, at some very basic level, it's that what you are doing is you're taking two of your let's say you're computing some n-point correlator. Okay. You take two of your correlator, or n-2 light operators, and then the rest of the two, you take it to be somehow as a part of your background. Okay. So they are like really creating a state. So therefore, you can think of it as being replaced by an appropriate density matrix. But okay, these are all words really. I mean, the mathematics is a bit more complicated. If you want to do it in quantum field theory, in quantum mechanics, you can get by with a little less work. That is true. But it's also useful. I mean, in terms of intuition, it's actually quite useful.
I see. And this is related to. I mean, so these operators can be then out of time ordered.
Yes, certainly.
The light
operators. I mean, for example, in some sense, when you create heavy states in CFT and you compute, let's say, heavy light correlator, right?
Yeah,
these are out of time order, because the heavy states you take to be t plus infinity, t minus infinity, and you're putting some other operators at two different times. So, I mean, you can do that sort of thing, but it's less interesting because you have really created a state, and now it's equivalent to computing a 2-point function in that state.
Right. But what you're talking about is different. You're talking about maybe like instead of 4-point functions, 3-point functions of the density matrix and some light operators.
Yeah, you can certainly do that. Yes, all I was saying is that if you want to make connections, typically with higher point correlation function, with quantities like operator growth or more information theoretic aspects, let me put it this way. then it seems to me that you need to make some special choices of some operators, a subset of those operators, to make those connections. So they are not always true for any operator. I mean, that is evidently true.
Okay.
But of course, what you said is also very interesting in the sense that if you, for example, when you take, let's forget about OTOCs. I mean, just correlators. When you take density matrix itself or the partition function itself as an operator, you compute correlators of the partition functions, then you start seeing very intricate structures of the spectrum of the theory. I mean, that is evident in quantum mechanics, for example, and nowadays people are also doing extensively exploring these things in quantum field theory, CFT, etc. So so yeah, I mean, I don't have anything precise, but maybe 𝗏𝗍𝗃 had something precise to say.
Yeah, I think this connection is sort of precise. So the thing which you mentioned is this Krylov complexity.
Yeah.
So that actually provides an upper bound to a number of other observables. So, and in fact, it can be proved that the growth of this Krylov complexity provides an upper bound for the growth of the OTOC.
Oh, yeah. Okay, good.
Yeah.
Yes, thanks.
So,
that is absolutely right. Yes, indeed. But what I think I was taking the question too literally, in the sense that whether you can actually connect the operator to the
yeah. In some physical sense, I mean, it is measuring something like that, because the OTOC we know that it is measuring the inability of one of the evolved operators to its failure to commute with another simple operator.
Yes.
This W and V, which you had.
Yes.
So yeah, and the Krylov complexity provides an upper bound for that.
Yeah. Indeed.
What is this Krylov complexity, 𝗏𝗃? I mean, what kind of correlator are you computing there?
So this is not actually given by some correlation function, but yeah, you choose some evolution protocol, and then it is sort of the average. It is a sum over probabilities of being in a particular state. Yeah. Well, I'm actually talking a bit about this. I mean, in my talk, like on Wednesday, I think. Yeah.
So just to sort of continue on 𝗏𝗃, actually reminded me of something in 𝗏𝗏. That's a specific model, but in 𝗏𝗏 there is a very precise definition of operator growth. That's just in terms of fields that are present in the model, and you can indeed show that definition, you can massage it a little bit to relate it to an OTOC. There, such a precise connection exists. So given a particular model, and if it's rich enough like 𝗏𝗏, for example, then this massaging, etc., can be done to probably to match it at that level. But yes, so what 𝗏𝗃 said, that certainly exists for always. That as an upper bound, there is always a connection.
𝗏𝗃, you have any more question?
Yes. Yeah. So my question was for Rajesh, actually. So is Rajesh around?
Nobody removed him. Left.
Yeah. Hi, Rajesh. Yes.
There's a background noise. Sorry, but yeah.
Yeah. So sorry, I wasn't present for your talk actually, but I saw your slides and I had this question even before. So this you have this correlation functions for twist operators in the symmetric orbifold, and then there is this relation in the large twist limit to this matrix model which you have. So there is one of the restrictions which is there is that the covering surface should be of genus 0, right? So I was thinking, like, if one can sort of lift this restriction, and can one make can one know something about, like, if one has, like, if the genus is greater than 0 or so on, like.
Yeah, so this has been actually studied from the point of view of the world. I think Lawrence Eberhardt has a paper on this localization property persisting even on higher genus surfaces, and therefore being the covering maps. Similarly, I think the twistor incidence relations also, I think there's a paper by Bob Knighton generalizing that to higher genus surface. But maybe what you're asking is from the point of view of the field theory, this connection to the matrix models, whether that exists at genus. So I think with Pranabesh we have discussed a little bit about genus 1. So it's a little it's somewhat interesting, and we don't have the complete picture, but at genus 1 there is a similar localization from the point of view of the world sheet theory. You know that there is a localization because the holomorphic maps, okay, so genus 1 but also to thermal ADS. So if you wish, you're looking at correlators, symmetric orbifold correlators of genus 0 covering space, but also corresponding to thermal ADS. So that's in some ways the simplest. You have a genus 1 covering map of the genus 1 surface, because there the holomorphic maps are easy to characterize. They are maps from torus to torus. So in that case, if you take this large twist limit, in this, so you can ask for the contribution of the partition function itself, even without correlators, even the partition function from the W twisted sector with large W. And they are localized on some very interesting points, discrete points in the torus moduli space. As far as I know, that's not a matrix model like, but it seems to be that again you can kind of cover the moduli space in the large W limit, okay, I think the short answer is that we don't have yet a complete picture, even in that case, which is the simplest one for higher genus, whether it would be very nice to generalize, I think, because in this case, what was nice is the covering maps were described by a matrix model. That was there may be something more which will involve more complicated matrix models, which involve, you know, like a periodic potential or something like that, as opposed to, because you have now some images, but I think the short answer is that that is still not known.
Okay.
Mm.
Okay. Yeah. Thanks. Yeah.
Arvendra has been waiting for a while. So, Arvendra, please go ahead.
Yeah, actually, I have a question with Anshuman. I don't see Anshuman around. So, is he there?
I'm here.
Oh, Anshuman, yeah. Very nice talk, actually. Anshuman, you were talking about the type 2 fluxes, no?
Yes.
They were of this odd ranks, basically anti-symmetric tensor fields, okay, in type 2b.
Yes.
What is the situation of the same kind of vacuage on type 2a, basically the even fluxes? Is there something very different story there?
Yes, it is. It's a different story. So and there is progress in understanding moduli stabilization, but here we can write down an explicit 10-dimensional solution. There it is, the internal metric is no longer something like a conformal Calabi-Yau or something. So there is progress, but not as much as in the type 2b case.
I see. I saw recently papers writing on this type 2a, massive type 2a fluxes and all that. People doing some work there. So, I mean, don't we get some kind of models there of the de Sitter type?
No, we can get models, but it is not, we don't know it as explicitly as in the 2b case, because I think, as far as I know, the 10D solution is not known as explicitly as in the 2a case.
I see.
But still there is, so more generally, there is constant progress in understanding moduli stabilization. 2B is probably the place where it is best developed, but yes, there's work going on.
Okay, thanks.
Okay, if you are done, Parvendra.
Okay, I can, if you allow me, I can take a small question to Rajesh, but this is just, Rajesh, you were writing that equation when the second page where you have left side some operators, on the right hand side you have vertex functions for closed string insertions. Actually, yeah. So you are assuming a symmetry, supersymmetry there in everything set up, or this will be even can be generalized to some non-supersymmetric backgrounds or something of that sort?
So I was trying to write down a statement which would be true for gauge string dualities in all cases where we know such a duality exists. So there is if there's a string theory dual to the corresponding quantum field theory. Now, most of the cases we know are, of course, supersymmetric, but I think the statement is more general, and probably there are general cases of non-supersymmetric backgrounds, and I would hope, let's say, for pure Yang-Mills also something like this should be true. But of course, we have much less. We don't have any at the moment, even any very good indication of what the right-hand side might be, the string theory or the same. But I would imagine it's a more general statement. Yes, that statement is just a statement about what you would expect for a general gauge string duality dictionary.
I see. But there are backwards in like you can write down ADS4 times S6 driven backward in a massive type 2A kind of gauge supergravities, which are not supersymmetric at all. But since being ADS4 and you expect boundary CFT there, which I don't know whether it is supersymmetric, but it should not be. But all that should apply there also, isn't that?
Apply there. Again, I should say this is for cases which have a string theory, perturbative string theory dual, because you need to have that the right-hand side was defined in terms of some perturbative sigma model. I'm not including cases like M theory or something like that. So those, whether supersymmetric or non-supersymmetric, are not included in this. So yeah, but the kind of cases you mentioned, I presume if these are type 2 string compactifications,
yes,
right?
Yes.
Presumably, if the string theory is well behaved, then whatever the dual field theory is, there should be some dictionary.
Okay. If Harvendra, you are done,
thanks.
Okay, I have a question for Anshuman actually. So this is regarding the flux compactification in type 2B that he was discussing, where he was talking about small double knot. So actually it so happens that the flux compactification in 2B is very much analogous to the attractor mechanism equations in type 2A. And in type 2A, you can also have non-supersymmetric attractors. And the stability of these attractors are very nicely analyzed by studying the minimal cycles. So I don't think there is anything analogous in type 2B. So if there is something which is analogous in type 2B, then it would be interesting to study non-supersymmetric vacua in type 2B itself. Do you think, I mean, studying small double knot which doesn't have supersymmetry is, I mean, has it been studied? What is the status of these vacua, or is there a mechanism that is there to analyze them and their stability?
So, I mean, this I mean, once you incorporate the scalar moduli stabilization at small w0, you will get ADS vacua, which are supersymmetric. So I guess your suggestion is that can these be analyzed by attractor?
Yeah, no, 𝗂𝗀, that is the standard 𝗂𝗀 scenario where you start with a supersymmetric vacua and then you break supersymmetry by adding NT-D3 brane. That is because because of the issues of stability, right?
Yeah.
But in type 2A, you can analyze the stability just by analyzing the minimal cycles.
Yes.
So, so then in type 2B also, if one can do similar things, then you don't have to search for small w0, which preserves supersymmetry. You can, I mean, there will be a whole lot of non-supersymmetric solutions also, which can admit small w0. And then that can be lifted to de Sitter.
Okay.
I don't know whether it's a reasonable question to ask.
Yes. Well, at least, I mean, I guess probably I'm not exactly getting the parameter space that you're going, but if you look at this LVS vacua, so there the ADS minimum that you get is non-supersymmetric.
Okay.
So now there none of the known alpha prime corrections destabilize this ADS vacuum. But in principle, there can be one alpha prime correction which can be dangerous for the stability. Now, the usual philosophy taken is that you will, if needed, you will tune parameters to keep it under control. But there is no evidence so far for such an alpha prime correction, the one that is potentially dangerous, in the sense that people have tried to look at toroidal settings and maybe orbifolds and wrapping branes, and so far there's no evidence for the existence of this alpha prime correction. But maybe what you are suggesting might be related to this thing, that how, if one is interested in ADS vacua, which are non-supersymmetric, in 2B, which is the LVS, then what you say could be relevant. So we could talk about this in more detail.
Okay. Thank you.
Alok has been waiting for a while. Alok, please.
You mean the one with two A's, right? Me?
No, because you raised your hand.
Yeah. Okay, no, the two of us, right? One with two, one with 1A. So okay. So yeah. I just so I wanted to actually make some comments in response to Prashanta's query, and maybe also it can be translated into a question to Anshuman. So the couple of things. The first thing is that if one is familiar with a story on one side, let's say in type 2B, one is interested in finding out the story in type 2A, and one is dealing with the compactifications involving projective varieties, which do possess a mirror. So usually it would be very surprising that that is not the case. So there should be some analog of pretty much everything on one side as well as the other side. With that said, I thought that when you talk about the superpotential, especially a la 𝗬𝗂𝗵𝗶𝗿, so the whole idea of flux times calibration would usually make sense when you have supersymmetry. If you don't have supersymmetry, I'm not sure that expression really has a whole lot of meaning. So you may want to consider generalizing the 𝗬𝗂𝗵𝗶𝗿 superpotential to address Prashanta's query about non-supersymmetric compactifications. So that's just a couple of remarks. And one last remark. I thought, I mean, I don't know if Sandeep is around, I don't know, but I mean, apart from, I mean, there are papers, I guess, though I haven't really not followed this up, but I know that there are papers by Kailash, Kachru, and McAllister, and probably also Sandeep, which have to do with, essentially justifying KKLT. But in terms of concrete type 2b flux compactification resulting in a de Sitter vacuum, I don't know if that is a settled question. I mean, I thought that is a very gray area, and definitely, I mean, I guess people like 𝗲𝗲 would say that that's literally in the swampland. So I'm not sure what one would mean. You can be optimistic that, okay, if it works, if the KKLT can be realized, you can first stabilize a Kähler moduli, then you go to the complex structure moduli, then maybe stuff can happen. Or, for example, if you're working with no-scale supergravity with the exclusion of high-derivative corrections, then you know that if you look at the superpotential, it is e to the k times mod dw squared minus 3 times mod w squared, where you would be summing over all the moduli. But if you have a no-scale supergravity, then the contribution to mod dw squared coming from the Kähler moduli precisely cancel the thrice mod w squared, and therefore it suffices to work just with the complex structure moduli. But that, as Anshuman, you know, that it would break down with the inclusion of high-derivative corrections, right? And the last remark is that if you are actually if you're actually doing a bona fide type 2b compactification with the inclusion of high-derivative corrections, you don't have a choice, but you know that the first non-trivial correction is going to arise at order alpha prime cubed, right? That's the paper by the Becker sisters and Michael Haag et al., right? So I mean, there's not a whole lot of choice there. So this is some remarks that I wanted to make. And so now Professor Marana, can I come to my query?
Yeah, please.
Okay, so Anshuman, I think I might have misunderstood or didn't quite hear it or understand, or all of the three. So you made some remark to the effect that something which was cubic in was it the pre-potential, or was it something was assumed, or you're going to be assuming that is to be dropped? Is that right? Something you said to that effect?
No, it is this. Okay, so let me just kind of put things a little bit in context for everybody. So, I mean, what I was discussing in what you're referring to is the recent construction by the Cornell group for small W0 for small. So choice of fluxes that leads to a small W0. And here I think they make, and in that limit, okay, so they say that if you work in the large complex structure limit, there the form of the superpotential is known to be polynomial plus exponentially small corrections. And the prescription is that you choose the fluxes so that this polynomial part is homogeneous degree 2. And once you have that, then there is essentially, depending on some properties of the exponentially small corrections, you can end up with a very small value of W0. So this is an explicit prescription, and you know, they actually do have many examples, and our work was also related to that in the sense that we can, the Diophantine equations that you get, we provide a systematic way to get solutions to this. So what this provides is one way to get vacua with small W0, and this is most likely not the only way. There are other ways. Now, on your comment about how this fits into the bigger conjectures about the existence or non-existence of de Sitter vacua. So if you look at, say, in particular, if you look at KKLT, there are certain things that we require, and one of them is small W0. So what this part of the story is that you now have explicit constructions for small W0. Now, this was known from statistical expectation. So if you did the usual statistical expectation, you would think that they are there. The improvement is that now people they'll tell you the exact Calabi-Yau's and the flux quanta that give you small w0. So this doesn't mean that the story is closed. There is a lot more to explore, but this is a way to get more concrete constructions, and eventually they should have effect on understanding the phenomenology of these systems. On your alpha prime correction comments, see, that is an n equals to 2 corrections. So now that you're turning on fluxes and branes, putting in branes, so there is the possibility of having other corrections. So some of those corrections are, if it was just the alpha prime Q corrections, LBS uses that, and there is, the vacuum is certainly stable. Even some of the n equals to 1 corrections, those that have been computed, to them, anything that has been found, LBS is still stable. But if you look at, I think if you just expand the Kähler potential and use general arguments as to the form of the Kähler potential, in principle, there can be one n equals to 1 correction, but that has never been found. I mean, people have done computations to see if it is there. In all examples, it's not there. If it is there, then some tuning would be needed. So this would be analogous to the tuning that you need for W0 small. Yeah, so that's from my side. Maybe I'm sure Sandeep has some comments.
Actually, I had some, I don't know, maybe there are several other people. I had a couple of things as follow-ups to Anshuman's. I don't know if I can go ahead. Maybe I should wait.
Yeah, Uttam has been waiting for a while.
Yeah, so. Absolutely. Okay, sure.
Uttam, please, if you are around.
Thank you again. Yeah, I have a very brief question for Rajesh. Is Rajesh around?
Yeah.
Rajesh is there.
Yeah.
Okay.
Yeah, I have to leave in about 3 minutes, unfortunately.
Yeah,
but
it's a very nice question and very brief. I maybe you had already explained it. I couldn't catch it. So, what is the significance of the tensionless sector in your analysis, Rajesh? How does it come about? If you can say a few words about it.
Free Yang-Mills is believed to be dual to the tensionless limit of the string theory. That is the point. The tensionless limit you can think of. In some ways, if you can almost define it as that corresponding to the free Yang-Mills point, because that is in some ways the point with the smallest string ADS scale, the point where there are massless higher spin fields, and so all these you can think of as the signatures of a tensionless string theory. So in that sense, in ADS, the notion of tensionless is captured by the dimensionless coupling, which is the 't-Hooft coupling, and that going to 0 is, if you wish, the notion of tensionless, because there is a radius of ADS scale and there is the string scale, and in some ways this is the small, when the 't-Hooft coupling is 0, that's sort of the smallest value of this. So so it is in that sense tensionless. Now, of course, you expect the dual world sheet theory to be also simplify in that limit. And that's indeed what we find in ADS 3, and we propose for ADS 5. It has this sort of level 1 kind of description, which turns out to be have a free theory, a free world sheet theory also. So, so in many ways, there are some of the features you might have expected of a tensionless limit, and you have in this case. Does that answer the question?
Right. I mean, yeah. Right. Absolutely. Thank you.
Okay. Thank you.
Okay, Alok, your turn.
Yeah, sorry. I just wanted to say this, that maybe I'm a little lost in terms of the terminology which is used. So usually when you talk about these polynomial contributions, one is not referring to the superpotential, but one is actually in special geometry referring to the prepotential. So I think that's probably what you imply, Anshuman?
Yes, well, you can, but you can, in this limit, you can compute, you start with the prepotential, but then you can use that data to compute the superpotential, and even the superpotential has this structure.
Well, okay. The other thing is that usually when you talk about these polynomial expansions, that's in the Kähler sector, the complexified Kähler. One uses the complexified Kähler class, and one has the linear term, the quadratic term, and the cubic term. And if one goes up to the non-perturbative contributions as well as alpha prime corrections, you have a shift, and you have this infinite series of worldsheet instantons modulated by the genus 0 𝗂𝗵𝗶𝗿 invariants.
Yes.
So that is the usual one, and in fact, the cubic term is the one which appears with the classical intersection number.
Yes.
So are you referring to the same expansion?
Yes, but in the 2V side. Okay, so here you are essentially using the mirror story. So these so that's why you are in the large complex structure limit of the Calabi-Yau. So you want, in the right conventions where the axionic fields are real, you want imaginary Z to be large, and that in the language that you're talking in, this translates to the large volume on the other side.
Well, usually the complex structure would be related to the exponential of the complexified Kähler class, right?
Yes, but I think that, so this is what I'll just say that you can, that's just, I think, a variable issue, but I think when you do the translation correctly, you can just, this mounts to imaginary Z much.
But okay, but essentially that let's probably not worry about Kähler or complex, but the bottom line is that this would really restrict, because as I said, this would, at least on the Kähler sector side, it would amount to having manifolds, Calabi-Yaus with vanishing intersection numbers, and that would severely restrict, therefore, the period in the corresponding algebraic geometry, and therefore the W. So, is one aware of such, let's call them 0 triple intersection Calabi-Yaus, which would contribute to a W0? In short, let me rephrase my question. So we have this old, if I recall, a very old paper by Denef, Douglas, and Floria, right? DDF 99 was it? Where they tried to enumerate compactification that would allow KKLT. So do we have vanishing triple intersection Calabi-Yaus in that list, which produce a very small W0?
So, so here, I think what is being used to get the small W0 in the construction that I described, which is the recent construction by the Cornell group, is that you're not doing anything with, you're not demanding anything on the intersection number. You are demanding something on the choice of flux quanta. And so at the end, this condition on the flux quanta translates to the Diophantine equations that I was describing. So the equations that you have, it involves the flux quanta, which I was treating as the variables, and then there are the classical intersection numbers. So you look at those equations as equations for the flux quanta, and thereby you try to solve for the flux quanta. So no additional criteria is being imposed on the intersection numbers. Maybe some choice of intersection numbers, you will find more vacua. That could be possible, but we're not assuming anything about the choice of the intersection numbers.
Maybe I'm probably not following the discussion, because just for one last clarifying comment slash query is that, the perturbative expansion of the prepotential's cubic term has the coefficients given by the classical intersection numbers. Yes. Unless they are non-zero, you will always have these cubic terms. So
no, that's in the prepotential. But what I want something about the superpotential. So I have to what I'm not demanding that the pre-potential is not cubic. I'm demanding that the superpotential is degree 2 homogeneous. So you have to compute, because see, the way this calculation goes is that from the pre-potential, you compute the period matrices, and then you also have the fluxes, which is again the integrals of the fluxes over the period, and then you do the G wedge omega. Okay, so when you do the G wedge omega, you have an expression for the superpotential, which has the intersection numbers and the flux quanta. And this is what you want to be degree 2. So it's not that you're demanding that the pre-potential is degree 2.
I see.
So it really is a condition on the superpotential. So if one way to say that is that you drop the exponentially small corrections in the pre-potential, and you work with just the cubic part, and with that you compute the superpotential, and with the superpotential, which is a function of the intersection numbers and the flux quanta, should be degree 2 in the complex structure model.
Right.
So that gives you an equation. This equation is given a fixed Calabi-Yau. This is an equation on the flux quanta, and that's what you try and solve.
Okay.
We shift Gautam. Gautam has been waiting for a long time. Gautam, you have a question?
Yes, thank you, Gan. Yeah, I have 1 or 2 questions for Ayan, very short questions. So will you allow that?
Maybe his collaborator will reply. He sent me an email.
Oh, he's not here. Okay. Then maybe I can talk to him directly. That'll be better. I mean, who is the collaborator?
Who is student?
Okay. Maybe I can directly ask him. Yeah, that's all right. That's all right. Thank you again.
Yeah, he sent me an email. So, Professor Alok Mishra, so when do you use the guillotine?
Oh, I see there are no further hands which are raised, so I think we can call it a day with your kind permission.
So you self-annihilate your hand.
Ah, yes. Okay. Yes. I apologize for that. Sorry.
No.
There we go.
So you should announce the closure of the session, right?
Okay. Yes. So all right. So thank you so much, everybody, for your kind patience. And so this brings us to the conclusion of day 1. So see you tomorrow, same time, and different link.
Good night.
Thank you so much. Bye-bye.
Okay.
Have a safe.
Thank you.
Stay safe.
Thank you, everyone. Thank you again.
Thank you. Bye-bye. Good night.
Good night.
So team, can I end the meeting with your permission?
Yes, sir.
All right.
Let me just stop the recording and the live stream.
Please, yeah, please do that. Please do that. Thank you so much. Okay, so I think I can end the meeting now.
Yes, sir.
All righty. See you tomorrow at the same time. Bye-bye. Good night.